Welcome to the 50th episode of the Richie Flow Nutrition Podcast. My name is Cameron Borg. In this episode, I had the pleasure of speaking with Scott Zimmerman and Robert Fosbury. Scott is an expert in optics and has focused his attention on quantifying the health effects of natural sunlight. With over 35 years of experience in the industry, Scott has unparalleled knowledge about how light interacts with systems. Scott is now a world leader in the optics of the human body and how light interacts with life. Bob is an emeritus astronomer at the European Southern Observatory and honorary professor at the Institute of Ophthalmology at University College London in Glen Jeffrey's lab. His unique perspectives alongside Glen Jeffrey have paved the way for a new understanding of how light, particularly in the near-infrared range, interacts with the body. His physics background has proved to be indispensable in understanding sunlight and how biological systems have evolved to use it. To celebrate 50 episodes of the podcast, I decided to have Bob and Scott back because they exemplify exactly what I'm trying to do with this podcast. As a result of our last conversation together, the two of them have joined forces alongside Professor Glen Jeffrey at UCL. They have been writing and presenting together about the importance of outdoor living as well as the detrimental effects of artificial light. So with all this being said, I really hope you enjoy the episode. All right, gentlemen, it's such a pleasure to have you back on. The last time we spoke was such an absolute highlight for me. Real big privilege to have had the opportunity to put you two in contact, and I'm glad it's been a very fruitful collaboration. So I thought we could probably start by just sort of catching up and seeing what you've been looking into since we last spoke. Maybe we can start with you, Scott.
Well, I mean, like I say, I really appreciate the fact that you introduced me to Bob and Glenn. We've been having collaboration on a regular basis, and it's kind of like an odd couple in that we have astrophysicist, optical engineer, and a biologist, and we're working together on something that I think has a big impact on health in particular.
Yeah,
Absolutely.
actually, Cameron, I think quite a lot of things have happened since we last spoke. It's been a bit of a rush in a way, and I think we've started putting this huge jigsaw together, and things move very slowly in the beginning. And as you put more and more pieces into place, they tend to get into place more rapidly. So to some extent, we've been a little bit swept off our feet in the rapidity with which we've made realizations of what's going on. And we certainly haven't got the whole jigsaw together. I think that will take quite a long time, but we're much closer to getting a sort of broad picture of what's going on. And what are the highlights of that? I think, for me, the highlights have been partly the realization that NASA are suffering with the health of their astronauts coming back from the space station, and the big paper that appeared in Cell a couple of years ago, which documents that and made us realize that, although we were aware of environments on Earth that were producing problems like hospitals, intensive care units, care homes, where people didn't get really any access to sunlight. We were aware of all these things. We've since realized that, an extreme example of a group of people who, ironically, have been in space for months and months and months on end, but they don't get to see the sun because it's too difficult for them to see the sun. And we know they live under LED lighting. I think we have a description of the lighting that they use. And although they're given circadian variations and so on, they don't have access. They're infrared starved, basically. And that was a big. It wasn't a realization for us because we predicted that would happen anyway. But to find out that it did actually happen, and it was characterized as mitochondrial dysfunction, was, of course, a big piece of knowledge for us. We suspect it's happening in other environments, like in submarines, nuclear submarines, which are under the sea for long periods of time. Those data are not so easy to get hold of, but we suspect it's happening in those environments as well. So that was one thing that happened. I think the other things that have happened, and they've struck, Scott and myself both together and independently, is that, there are so many things associated with broad spectrum light that have been cut off from us in the modern built environment. And, the breadth of the effect of this starvation of the full spectrum of sunlight have been profound and growing. This is something that's getting worse continuously, and in ways which we'll probably explain a bit later on. I mean, they could get very much worse due to things that are happening around the world in control of lighting, both external lighting and lighting in the built environment. The other thing that's, happened to me is trying to understand what effect the light is actually having on biology. I mean, what are the interactions between photons and life, the whole biosphere, not just humans or animals, but the whole biosphere. And this, I think, we've made a fair amount of progress and have a clearer general idea of what these interactions are and how they're occurring. And hopefully we'll be able to explain this today in a bit more detail. We've been doing some experiments ourselves. I mean, we don't have enormous resources for doing experiments in complex situations, complex laboratories and so on. But I mean, I've been doing some experiments of passing light through my body, my hand, and I've seen things there which I think are actually very important. It's difficult to make them publishable at the moment because this is in my study at home with my own spectrometer. We need to do a lot more experiments, but I think the insights we're getting from this are really quite deep, and we need to verify these certainly before we can go on. But I think they're strong indicators of what's going on. And so I think we can present a clearer overview of what's going on today than we could last time we spoke. I think that's what I can say.
Yeah.
And I'd add in that I think we're also, my focus has always been on mechanistic effects, and what we're now showing and understanding is that there's a lot of structure that's built into the body that we haven't really taken into account in a lot of the papers to date. And it's just absolutely fascinating how the body is building structures that can absorb or redirect or localize all the different wavelengths in the body in ways that we haven't, taken into account yet. So
that's really fascinating. I love that, and what I love about what you said, Bob, was about how there seems to be this clear dichotomy between what you're talking about with this broad spectrum effect, these light-life interactions, and the circadian people, with what's happening in space. They're using these LED, and I believe they're quite sophisticated, LED setups that they've got that are trying to make a circadian environment, but they've missed the whole invisible side of the equation. And it really, why I guess what you guys are trying to do is trying to unify those two things together and say, look, the reality is the full spectrum, the way that we have evolved, the way that life has been adapted to it for over 4 billion years. That's really what we need to be focusing on. And
yes, well, I'd really like to start on that as an introduction to the topic, and reiterate what you just said. We have life on Earth has evolved under sunlight, and although the sun has changed a little bit in that period, it hasn't changed very substantially. And the important thing about sunlight is that it's a source that radiates because it's hot. It's a thermal source, and it emits a blackbody spectrum, a Planck spectrum. And of course, we've now adapted over this very long period, the whole lifetime of life on Earth, 3.5 billion years or whatever it turns out to be. We've adapted to this thermal source, and we remained adapted to this thermal source until the middle of the last century. And that was the beginning of the downturn, I think, in the reaction of life, especially us in the built environment. Just going back to the circadian and rhythm and the space station, I mean, the point about the lighting on the space station, it's still white LEDs, although they changed the color temperature. The color temperature is, for an LED, is a fairly meaningless quantity.
Yes.
I mean, the LED spectrum is so different from a thermal spectrum that it doesn't mean terribly much, but they are infrared dark. I can use my camera with all my LED lights, my infrared camera. I can use my infrared camera with the LED lights on in my room as if it's in darkness, if I'm measuring the infrared. So it really is infrared dark. And so when we talk about ratios between short spectrum light, short wavelength light, and long wavelength light, we're not talking about, the difference in the ratio from 1 to 1. We're talking about a difference between 1 and infinity, or 1 and 0, whichever way you look at it.
Yeah.
I mean, it's a huge difference in the proportion of light from different parts of the spectrum, and that's what's so important. And I think if we focus on the recent history and the evolution of lighting, I mean, I think the first commercial fluorescent tube was in 1938, around then. And, fluorescent tubes are not completely infrared dark, but they contain precious little near-infrared light. And then, of course, in 1996, we had the first commercial white LED. And since then, many of us have been living in a built environment which is lit either by fluorescent tubes or by white LEDs. And so we have become starved of infrared light. And it's, this starvation is, I think there's quite a good analogy with the well-known disease of scurvy and the early days of exploring the planet by sail. We know that these sailors set off in their sailing ships to head for Cape Horn or the Cape of Good Hope. And after a few months at sea, they started getting sick. And although it was realized fairly early on, the cause of this sickness was the absence of vitamin D. It took, I know in the British Navy, it took 100 years before they actually reacted to this and gave the sailors foods rich in vitamin C. Did I say vitamin D? I meant vitamin C.
People know what you mean.
Yeah, and so, we're currently being starved of near-infrared radiation. And the effects of this are not immediate. They appear over periods of time. And, it is over decades that we're seeing a decay in general public health, which is, in the general public view, is not really understood. And, I'm sure you've had podcasts about junk foods and ultra-processed foods and so on. There are many factors involved with the changes in public health. But I think the light issue is probably one of the basic underlying factors in this. And it is one of those factors that we can actually do something about. And the other thing that's happened over the time after our previous talk, we have had a lot more contact with people, not so much in the scientific community, but people in the applications community, like architects and lighting manufacturers, who are, of course, very interested in what we have to say about the effects of lighting on health, because, these people want to make healthy environments for people to live in. And if there's evidence that they're contributing to unhealthy environments, they certainly want to change. And so we found that we've had a lot more contact with the architectural community than we had before. And these people respond to us with much more interest than some other parts of the community.
I think this problem is...
Carry on.
Oh, I think this problem is even more pernicious than the ultra-processed foods, for instance, because I think most people are aware that processed foods are bad for them, but almost no one is aware that the lights that they have in their home are damaging their health. So, it becomes such a pernicious issue because people aren't even aware that it's a problem. So how do we even get people to be aware in the first place before we can even start changing it? And I think there's so many strings I want to pull here, but there was a graphic that I really like, and I use it in a lot of slides that I use. And it's basically got it overlays the spectrum of, full spectrum sun, and it's like, 4.3 billion years. And then, 100 years ago, we get the incandescent, which has this, predominantly in the near infrared. And then, 20 years ago, we have the LED, and they're overlaid, so you can see how different they are. And I think this really points out the magnitude of change that we have gone through in evolutionary, the blink of an eye. And, the fact that this has happened so quickly and in a way that our vision is not capable of understanding. We never needed to we never evolved to need to be able to distinguish between broadband emitters and narrowband emitters. Never in nature did we ever have to make that distinction. And it makes me think about something that was in one of your earlier papers, Scott, with regard to this sort of Goldilocks zone that we're looking for in, reactive oxygen species. Too little, and it's no good. You can't have too little because they're important for signaling and cell regulation, but you also don't want too much because that's going to cause this runaway problem. You want to find this place in the middle. And I think we're missing a lot of that because of the impact that particularly the longer wavelengths are having on the mitochondrial dynamics and the flow of energy. So, how do you see this conversation tying into, how are we translating this to get people to understand that this is even a problem in the first place?
Well, it's a combination of it. Is it a problem or not a problem? But it's also a problem of fear. I mean, what has happened is that most people, you mention the word sunlight or sun, they immediately jump to, I'm going to get skin cancer or something like that, because there's been so much emphasis by the dermatologists and things like that, people like that, to say that the sun is bad. And unfortunately, even the data that we deal with is usually looking at the spectrum as direct sunlight. What really needs to happen is people need to understand nobody's asking them to go out and lay on the beach and turn into a French fry. What we're saying is that the body has adapted to take into account primarily its surroundings. And if you look at some of Bob's work and the near infrared photography, you see that all our surroundings are strongly absorbing in the visible and reflecting in the near infrared. And so the ideal situation is that people spend more time in nature, not under a tree. As Bob likes to say, Isaac Newton didn't invent gravity because an apple fell on his head. It was because he was sitting under a tree. It's unfortunate, but there has been such an emphasis. There are people that don't walk out the door without putting SPF of some type on. All the makeup now has SPF, which makes absolutely no sense, especially for women who have very dark skin. They have almost zero chance of getting melanoma, but they're having a hard time generating enough vitamin D and things of that nature. So I think that what we're trying to get people to understand is that, a good walk, and everybody likes forest walk, forest bathing. Those words are all key. Well, there's actually a real reason, and it's because it is absorbing. It's like nature's sunglasses. It's absorbing the UV and the visible, predominantly, and strongly reflecting the near infrared. So you're basically in an environment that is near infrared rich. And, what appears based on the work that we've been doing and others is that the body uses that high level of near infrared to optimize a number of biological processes. And when you took it away, and as Bob said, we didn't just do a little, we did 180, where literally for some people in nursing homes and in the, even this new stealth vessels for the Navy, the problem is they have no portholes anymore. They aren't getting anything. And so they're seeing these effects where, just 60 days out, coming back and sailors are getting sick, are feeling raunchy. And those are the last people we want to be having, not feeling at their best and optimum. So it's almost like we've created this environment that is the actual antithesis of what actually happens in nature. And I think that's where a lot of
getting worse. And it's getting worse, Scott, isn't it?
Yeah. Absolutely. And it's not like that they're doing it just to be nasty. There's a trade-off here that's going on. You can't just shut down 90% of the solar spectrum without negatively impacting the body. Yet, if we do that via lighting, via window treatments, via displays, then you can do it and save a little bit of energy, I believe. Although even that is becoming into question because there's so much problem now with artificial light at night and things of that nature. So I think that it was great intent. I think the DOE and other people had good intentions, but they ignored a fundamental part of nature. And I think that's the thing that I find the most fascinating is the deeper we dig, the more it's clear that the body uses the near infrared to generate an optimum performance position, and including your innate immune system and mitochondrial function. I mean, Glen's work where he showed that he could, essentially improve the efficiency of mitochondria conversion, using just a small amount of, near infrared or deep red light. I mean, we know we know it's beneficial. The question is how do we convince people that it isn't that scary old sun that's going to give you melanoma, because that's what actually happens 90% of the time you have this conversation.
Yeah, I'll actually introduce a little anecdote here, which people might find amusing. One of the things that happened during the time since our previous talk, I looked at a mushroom, and then I subsequently looked at a number of mushrooms. And of course, mushrooms are the seeding bodies of the mycorrhizal network, and they come up generally in the forest understory, under the trees. And I put one of these mushrooms on my spectrometer and shone white light at it, and it glowed like the setting sun. And I thought, what's going on here? And it turned out that if I used an integrating sphere, where you use to measure reflectivity, non-specular reflectivity, if I put a mushroom on my integrating sphere, it was the most highly reflective surface I've ever found in nature. It was over 90% reflective. Now, that's not really reflective. It's not reflecting from the surface of the mushroom. It's backscattering of light that's penetrated the mushroom. And I suddenly realized that these mushrooms are designed to come up in the forest understory. They have a nice domed or flat top. They're covered in leaves in the forest understory. They don't get so much visible light coming down, but they get all the near-infrared light, which is scattered from the leaves. And so they're bathed in a 180-degree hemisphere of light from the forest canopy. And what are they using that for? They're using that to drive their mitochondria, give their mitochondria more oomph to make spores and reproduce. And in fact, I think if you look across the spectrum of life, you'll find that the process of reproduction is very energy demanding process. And this near-infrared light is a major contributor to the success of reproduction. Seeds in plants, and I could tell you some amazing stories about seeds in plants and the way they get infrared radiation.
I think that's
I don't have
mirrored.
time today, but for the next time, I can tell you amazing stories about this. So I think we're talking about the whole biosphere. We're talking about almost all of life on Earth is, of course, driven by solar photons coming in, getting through the atmosphere and producing this rather broad spectrum on the ground. It's not the full solar spectrum, of course, because the ultraviolet's absorbed in the atmosphere and parts of the further out in the infrared are absorbed by water and carbon dioxide and ozone and things like that. But this broad spectrum reaching the ground is interacting with life in ways which, if you looked at it in detail, blows your mind. Life is highly adapted to capture and utilize the light across this spectrum. We don't know all the mechanisms yet. It'll probably take a long time before we can tease out all the mechanisms because they're very deeply quantum mechanical. They're likely going to be very difficult to understand in detail. We know quite a lot about photosynthesis now, and that blows your mind. If you look at the details of how light, photons from the sun, actually get into this electron transport chain, make the battery, and produce sugars as an end result, it's an amazing story of quantum processes. And it's so elegant and so beautiful, but quite difficult to figure out and understand. So, the mushroom story struck me quite profoundly because I realized that, we have these ultra well-developed structures all around us that are utilizing more than just visible light. Why are we so focused on visible light? Well, obvious reasons, because it's the only thing we can see. But I think it's interesting to think that if you wanted to see in the near infrared, if you had a detector in your eye that could see in the near infrared, it actually wouldn't work because the light gets in through your eyeball as well as through the lens. You don't have to shine the light through the lens. It gets in through your head, through the eyeball. And also there's a very fundamental property of materials in that visible light gets absorbed because atoms and molecules can be excited by photons of reasonably high energy in the visible, which it can excite these molecules or atoms to higher energy levels. And the fact that you excite atoms or molecules to higher energy levels makes them colored. So all the pigments that you see, the chlorophyll, the hemoglobin, all the artificial pigments are pigments because photons of visible light can excite electrons to higher energy levels. If you move a little bit into the infrared, beyond where chlorophyll it becomes transparent, beyond 700 nanometers, there really aren't many pigments. The pigments have gone away because these photons don't have enough energy to excite these atoms and molecules to higher levels to make colors. And so there's a radical difference between shining light into life in the visible, where the first thing the photon will do when it hits your hand or your head, or it'll get absorbed by a pigment, hemoglobin probably, or other melanin or something, it'll get absorbed. If you shine an infrared photon at your body, it's much more likely to be scattered off a cell wall without change in energy than it is to be absorbed. The absorbers are few and far between, and they're very, very weak. So if you shine light onto your body, the photon will penetrate to, say, 1 millimeter in depth because there aren't many pigments, but then it'll scatter off a cell wall and it'll scatter around many times. It can scatter tens, maybe even hundreds of times before it actually comes across something that will absorb it because the absorbers are so weak. But it'll either escape out through your skin again, or it'll go deep into your body. So this is the way light gets deep into the body. It scatters into your body. It penetrates the skin, short distance, and then it gets scattered, and then it gets scattered again, and either it comes out or it goes deeper in, and it'll scatter many times. And it's almost as if this photon is looking for something to absorb it. And when it finds an absorber, it will get absorbed. Fine, you've lost the photon. But these very weak absorbers, I think, are very, very important for biology. And
Yeah.
that's an
And
absolutely critical factor. But,
yeah, and I think that people underestimate that we really are, the body is, when we're walking in nature, a solar collector. It's collecting, but it's doing it, as Bob says, some wavelengths go deep into the body, some are just, unfortunately, almost all our understanding or the trials that have been done all talk about milliwatts per centimeter squared on the surface. They don't really look at the three-dimensionality. And that's what I think is so amazing about Bob's picture of the hand.
Yeah.
Is that if you use the existing lore and the models that people have and their understanding of how optics works, everybody, if you look, near infrared only penetrates a millimeter into the body.
Mm.
So how does Bob get a picture where it's going inches through the hand and localizing in the blood vessels? You know, the two, you can't have it both ways. And what we're finding is that the longer wavelengths do this walk through the body, finding something that has a weak absorption. And what it does is it basically changes the photon density, making it, you have to think about it in volume, as like I say, as photon density rather than photons per surface area. So.
Yeah, just think what happens. So imagine your hand sitting there, and you've got the sun shining down onto your hand. The photon goes into your skin by, let's call it, a millimeter, and then it scatters, and it scatters many times. So it's staying in your body much longer than it would if it went straight. If your hand was transparent, it would go straight through. But it's scattering many times, and each time it scatters, it's staying in the body longer and longer and longer.
Longer and longer.
But you've still got these photons coming from the sun in. So you're collecting photons, and you're increasing the photon density inside your body. It's like you're blowing up your hand like a balloon with photons. So the photon density inside your body can be higher than the incoming photon density from the sun. And all of those photons are going around. It's like a gas of photons in your body. All they're going around looking for an absorber to absorb them. And so, that couples the sun to your body in a very powerful way, which amplifies the photon density inside your body. But to go even further than that, and this has been blowing our socks off over the last few months talking to Scott about this, we know in plants, there are nanostructures which trap light. This has been well publicized in the scientific literature. There are nanostructures in plants and animals, structural coloration. There are nanostructures which essentially interact with light in a way that sets up standing waves, for instance, and keeps the light in the body for longer. This is another amplification process. And if we can see these in chloroplasts in leaves. There are beautiful structures in leaves which trap light in ways which I'm sure Scott will describe a bit later on, mind-blowing ways. But if you look at electron micrographs of animal tissue, human tissue, animal tissue, you'll find at the cellular level, there are nanostructures with regular layered geometry. And the separation of these layers are such that they will interact with infrared wavelengths and essentially trap the light and guide it into a place where it can be absorbed. So we have all of these factors. Once these photons get into the body, there's an amplification due to the length of time that the photons stay inside the body, which is quite long. Still very short, of course, in absolute seconds, but it's very long compared to the light travel time through your body. And there are all these capturing nanostructures in your body which make sure that the light is fed into places where it can be absorbed. So as Scott said, it's a beautifully designed by evolution process of capturing and channeling light into places where it can be absorbed. And we can actually do calculations which, compare the light coming in from the sun and try and calculate how much of that light could be absorbed by a particular absorption in a molecule like oxygen, and ask the question, is it possible to absorb in this oxygen the sunlight coming in from the sky, given the density of oxygen molecules in the body? And if you do the simple sums, it doesn't work out. You find yourself 100 or 200 or so factors short of being able to absorb this light. But we actually see this light being absorbed. And the reason we see it being absorbed is there are these amplification factors in the transport of light into the body and trapping in nanostructures, which makes up this factor that was missing. So we actually see these absorptions going on, and we know that the light is being absorbed by these very weak absorbers in the body. And these can be absolutely critical. I mean, you can excite reactive oxygens directly with sunlight in a particular position in the body because of these amplification factors.
I guess, go ahead, Cameron.
Oh, I was going to say, I saw a video the other day of someone who had quite a small kitten, and they had a flashlight, just a regular, white light flashlight, and they put it on the kitten's head. And of course, out of the eyes came all the red light, and it looked like, Darth Vader, because all the red light was coming out of this kitten's eyes. And I thought, obviously this person wasn't thinking what I'm thinking, and I'm going, isn't that a brilliant display of what's going on with these longer wavelengths? How deeply they're getting in because of this scattering effect. And yeah, like you said before, we actually couldn't have these near-infrared receptors because the light goes straight through. And that's a perfect example. And I've been quite enamored with the biophoton research recently. And one thing that they all state is how difficult it is to distinguish between true biophoton emission and delayed luminescence. And some of these papers talk about having to have people dark adapt for up to 120 minutes to eliminate the delayed luminescence. And I'm sitting there thinking, how on earth is ambient light hanging around in the body, bouncing around for that long after the after the exposure, that you have to be dark adapted for 1 to 2 hours before you can completely eliminate that signal? And this is something that I mentioned to John Mitrofanis. I spoke to him recently. He's just starting to do biophoton research. And I said to him, it must be very difficult trying to deal with this delayed luminescence problem. I think there are ways of dealing with it now. But yeah, just the fact that the light that we're exposed to in an ambient environment is hanging around in the body for so much longer than we would think. And like you said, when we're out in the sun, the photons that we're being exposed to are spending a lot more time in our bodies than it takes for them to hit us. So we're basically accumulating, like you said, blowing up like a balloon, filling up with these photons. And I have no doubt that there are all of these different type of quantum processes going on inside with the photons interacting. And perhaps now would be a good opportunity to talk about what's actually going on with all of these different weak absorbers. How are these longer wavelengths of near-infrared and infrared actually shifting and shaping the way that the organism is able to stay in a homeostatic range?
Well, I guess, can I get back to one thing before we go too far? Because it's kind of one of my pet peeves or whatever. But I think that what you're talking about is important, but I think we have to get back to some of the fundamentals from the standpoint of one of the things that we're struggling, as I said, is that how can you say the models be saying that something's 1 millimeter is as far as near infrared goes into the body, and then you see Bob's picture where it's going inches. And I think one of the things that needs to happen is that we need to stop with the improper measurement of optical absorption coefficients. And the thing I'd like to get people to think about is that if you take a laser pointer and you put a clear, ice cube, and you put a detector on the other side of the ice cube and you set it up, other than the Fresnel losses, you basically have 100% transmission to that detector. If I replace that that ice cube with a snowball that has the same dimensionality or whatever, and I shine that same laser through that other detector, you're going to see almost no light go through. There's no difference in the absorption characteristics, but what there is scatter. And that's what I think people need to understand. You cannot make a measurement and come up with an absorption coefficient unless you take into account the effect of the scatter. And that's what's so elegant about Bob's picture is that it's showing that there's all this scatter. Time constants, how long the photon, you're not talking about very long, but what you're talking about is that the photons are being absorbed and in a different way, and that they are allowed to come into the body. Once you get into the body, you're now in a high refractive index environment. Our interstitial water fluids and all that at 1.3. It's like any other thing. Once you get into a light guide, and that's what we really are, it will bounce around until it gets either scattered out of the situation where it's at a high enough angle that it can escape, or it's going to find, as Bob says, a weak absorber of some type. And that is what is the elegance of the entire body, is that we are like that snowball in that light is being distributed out over a wide volume and finding these absorbers. Now, based on this new stuff we've been looking at and understanding some of the structure, Bob on his Flickr feed has some stuff about shows butterfly wings and blue jay feathers. We're seeing that the one thing that nature has an advantage over, and I'm really kind of jealous about, is that they can make nanometer type features. Once you introduce even a single periodicity between a high index and a low index at a scale of nanometers, 100 nanometers, 200 nanometers, you now have localization. So you get all these optical effects where you have light trapping is one way to look at it. And like I say, I just put out a LinkedIn post about what I found was probably the most elegant optical system I've ever seen in my life. And it's this chloroplast Bob was talking about. And once you start seeing that, you have to immediately convert from your way of thinking of standard geometric optics and start thinking about wave optics. And that's what the body has been doing at a level that we can only dream about, to be quite honest. And, we can talk about it if you want, but what happens in the chloroplast, I believe, is fundamental in how the body uses its ability to generate nanometer levels of structure to put light right where the chromophores need it to be, and at the same time change what actually comes into things like leaves and stuff like that. But anyway.
When Scott thought of this, he had to have a cold flannel on his head for days afterwards. It blew his mind. No, it is stunning, and I just want to come back to the delayed luminescence, and I think we should make clear to people that these are two similar effects, but they actually have quite different. We're talking about the photons coming in and bouncing around. It's still the same photon coming in. The delayed luminescence is, generating an excited state in a molecule, a long-lived excited state, usually a triplet state in the molecule, which has a long lifetime, and that energy can stay there and become a photon later on. It's a bit like the air glow in the air, not the aurora, but the air glow you see in very dark sites. You see the oxygen in the air glowing red and green. You see it from the space station. You see the green air glow close to the surface, and you see the red air glow over a much higher range of heights above the ground. This is stored photon energy. It's a photon from the sun that's been absorbed and then engineering itself into a long-lived metastable state in the atom that can come out later. You can absorb it in the daytime and it can come out at night later and produce this glow. So, you can store photon energy in the body as well as scatter it around for long periods of time. But they're two somewhat different physical processes. What we've been talking about up until now is the photons coming in, bouncing around, getting trapped, and then finally being absorbed. So the same photon in a sense.
Yeah.
In a sense, it's the same photon. It's the same photon energy. But the photoluminescence in the body, if it ends up in a metastable state, it's an excitation of a metastable state. It won't become a photon until later.
Right. And is that happening in a nonlinear fashion, like as in the photon that's emitted is not necessarily the same wavelength that is the one that excited it?
Well, I think it's because you excite let's call it a molecule. You excite a molecule to a given state,
right? And
then if it's a vibrational state, it would rapidly drop down again to an electronic, the basic electronic state, and it will emit a bit of heat. And then there's a chance of it swapping over to a place where it can't immediately drop back to the ground state again. And so, the energy of the original photon will be higher than the energy of the photoluminescent photon.
Right.
When it goes down, when it immediately gets absorbed into a vibrational level, it'll drop back down to the electronic excited state, and then it will either fluoresce, i.e. drop back down to the ground state and emit a fluorescent line, or it will get transferred to one of these metastable states, and it will wait there for much longer before coming down. All of those photons will be of slightly different energy.
Yeah.
I mean, and the luminescent photon will be the lowest energy, but it'll come out later.
Mm-hmm. So
what's really need a diagram to explain that? But
I think I get it. Yeah, so there's all these different pathways back down to the ground state, basically. Yeah. So back, just want to get back to this idea of weak absorption and the fact that most of the molecules inside of us are weak absorbers, and that sort of makes this photon trap, for instance, it makes it more likely that near infrared photon is going to make it to a strong absorber at some point, but take quite a long path along the way. And what is the route of translation? How do we get from knowing this to how this affects, like Glen showed with the impact on blood glucose spikes earlier this year in his publication with Mike Powner? How do we bridge the gap between the phenomenon that we notice with this scatter effect to this is where the rubber meets the road as far as health outcomes come? Yeah.
Well, let's. I have a way of trying to explain this, and I think it goes back to quite basic physics. If you consider your body, you're sitting in the dark, so you're in a state of homeostasis. Your body is stable. It's at a given temperature. You're being fed with nutrients at a given rate. So you're in a stable situation. You're living stably without very much light. Okay? So it's nighttime. It is nighttime.
I do have one of Scott's beautiful bulbs here.
Oh, right. Okay. almost nighttime. So you're in a state of homeostasis. Now, the medics and the biologists think of homeostasis is that you have a body temperature, 37 degrees centigrade. You have a pH of the fluids in your body at a particular level. You have a certain flow of nutrients. You have oxygen coming in. You have carbon dioxide going out. So there's a balance between all these processes. And in some sense, you're in a state of thermal equilibrium, or you're close to a state of thermal equilibrium. Everything's hunky-dory. The only energy you have available to you is your nutrients coming in and the temperature of your body, which provides a low level of random energy for knocking molecules around and perhaps exciting them to very low energy levels. If you go out into the daylight, you have sun shining down to you. And the characteristic of sunlight is, the photons that you're getting from the sun come from a much higher temperature source. The temperature of your body is 37 degrees, and that's about 300 kelvins, the temperature of your body. But the temperature of the sun is nearly 6,000 kelvins. So it's much, much hotter. So the messengers that are coming to you from the sun, the solar photons, have the characteristics of a high energy radiator at a much higher temperature than your body. Now, okay, the photons are coming all the way from the sun, so the density of photons reaching your body through the atmosphere onto the surface and entering your body, the density of photons is much, 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 much lower than the density of the photons in a black body at 6,000 kelvins. So obviously much lower than the density of photons inside the atmosphere of the sun, where the photons came from. But they retain this character of the high energy, the high temperature of the source. So you can imagine your body being in homeostasis in the dark at a temperature of 300 kelvins, suddenly being given a source of photons getting into your body coming from a much, much higher temperature. What does that actually mean? It means you're not necessarily getting much more energy in your body. It won't upset the temperature of your body. It won't suddenly make your body hotter. But when those photons from a high energy source start interacting with biomolecules, they can excite. They're high energy photons. They can, although they're still in the infrared, they come from a high energy source, and they can excite those biomolecules into low-lying energy states. And we often call these ground state configurations. There's a basic ground state, the lowest energy state, but there are a number of other energy states above the ground state, which are only slightly displaced from them. And some of these are vibrational states, which, you get vibrations between the bonds in a molecule. But there are other electronic states which are close to the ground state. And the best example of this is the oxygen molecule itself. The oxygen molecule has a ground state, which is actually, in quantum mechanical terms, is called a triplet state. And that's quite unusual for a molecule to have a lowest level state, which is a triplet. And the singlet states, which are normally the ground states, are actually above at a higher energy in oxygen. And there are a couple of singlet states above this ground state. And an infrared photon can excite this oxygen molecule from the actual ground state, the triplet state, where all the electrons are sitting. It can excite those into one or other of these singlet states. And what happens what does that actually do to the molecule? Well, it makes that oxygen molecule into what we call a singlet oxygen. Now, you'll have heard of a singlet oxygen. It's one of probably the most basic of the reactive oxygen species. It's far more reactive than the triplet state. And so if you've got an oxygen
Is that because
molecule,
of the spin states of the unpaired
it's the spin
electrons?
states of the electrons, yes.
Yeah.
It's the alignment of the spin states of the electrons. And that means that, when you have a singlet oxygen, it's far more electron hungry than a triplet oxygen. And, I made this hypothesis that if you were sitting in a critical place in the energy processing chain in the mitochondrion, called the electron transport chain, where you're changing the voltage of electrons going up a chain, so you can pump a proton across the membrane to create this electric potential, which drives the generation of ATP, the energy currency of the cell. If you hit that, there's an oxygen sitting there waiting to accept an electron, a series of electrons, in fact. There's an oxygen molecule at the end of this electron transport chain before you push the final proton over the membrane. waiting to accept an electron from the cytochrome C, the last enzyme in the chain, what would happen if you had a photon came in, an infrared photon, and excited this triplet oxygen to a singlet state? It would be far more electron hungry than it normally would be. Therefore, my hypothesis is that you would grab the electron with far greater energy. You would jump across and grab the electron with great alacrity because you're in the singlet state. And maybe in that way you can speed up the process of the electron transport chain. This last step where you're waiting for the oxygen to grab the electron, this very last step in the process is apparently the rate limiting reaction in the whole of the electron transport chain. So if you could speed this up with a singlet oxygen, you would sort of basically speed up the whole electron transport chain. And I asked this question of one of the real experts on this process, and the person who actually understood the rotation of the ATP synthase, the enzyme that makes the ATP from the voltage difference across the membrane. I asked him what would happen if you excited an oxygen atom in the triplet state to a singlet state. And he looked away and he thought about this and he said, that's a very interesting idea. I hadn't thought of that. So, I don't know how this would work in detail, but I think it's an example of the kind of thing you might do with these. And this is one example of one molecule. There are many molecules, many biomolecules that have low-lying states, which could be excited slightly by the incoming infrared photons, which would probably make those molecules react much more quickly than they would. So the whole series of redox reactions that you have in metabolism, in respiration, that whole series of redox reactions could be accelerated by this flux of near-infrared photons coming from the sun. So you would, in effect, generate a new state of homeostasis, which included not only the temperature of your body and the pH and so on, but included your own particular connection with the surface of the sun, which would be this flux of photons coming down from sunlight and forming a radiative equilibrium within the mitochondrion. So you had a constant flux of solar photons, infrared photons, coming into your body and changing the state of equilibrium, changing the homeostasis in your body to be more reactive, to be more able to generate energy more rapidly with within the mitochondrion. So what you're really doing here is you're actually putting out feelers and you're establishing a distant contact with the surface of the sun. And that's contributing to the detailed biochemical state of the interior of your body. In a way, it's acting like an enzyme. The way enzymes can speed up chemical reactions by very, very large factors. We live on enzymes. All life lives on enzymes, doing their stuff all the time. In essence, the photons coming from the sun, they're not actually enzymes, but they're doing the similar thing to enzymes. They're making the body work better, faster. So that.
Are you suggesting? I just want to see if I'm understanding this correctly. Are you suggesting that there is a qualitative difference between the photons that come from the sun and even the equivalent wavelengths that are coming from artificial light? Is there a qualitative difference in those photons?
No. It's simply that the infrared photons coming from the sun could not be generated inside your body. They're way higher energy than anything that can be generated. I mean, the photons generated inside your body would come out at 10 microns in the mid-infrared. And we're talking about, less than 1 micron wavelength. So these infrared photons, although they're lower energy than the light that does photosynthesis in the visible, or the light that generates vitamin D in your skin, they're still far, far higher energy than the energy of the temperature associated with the temperature of your body. So the high energy, they're sprinkles of high energy units coming from the sun, even though they're only in the infrared, but they're at short wavelength infrared, which is still a lot of energy as far as biomolecules are concerned.
So it seems like what's happening is that it's increasing the efficiency of the basic charge separation within the mitochondria, and this sort of makes me think of what you were talking about last time we spoke, Scott, about Zostaro's data showing the water absorption bands. And how those absorption bands are coupled with reactive oxygen species generation in the infrared, and I think the increased production of reactive oxygens on exposure to near infrared and infrared is probably a sign that flux through the mitochondria is more efficient. And of course, the more energy you're making, the more reactive oxygens that come along with that. Is this sort of how you're seeing it as well? That these wavelengths are contributing to the increased flux, and that's coupled with what we're seeing with the reactive oxygen species generation in those bands?
Well, I mean, clearly, based on Glen's work and other work and all the work going on in red therapy, there is a biological effect associated with longer wavelengths. The fundamental rule or the fundamental thing that's going on in our artificial environment is that the assumption is there is no biological effects.
Yeah.
And therefore, why do we need it? We took it away. And that's where I think what we're finding is that I think there was a general feeling that I remember talking to a photochemist, and he said, well, nothing happens beyond at wavelengths longer than 480 nanometers because it can't randomly break a molecular bond. Well, that is incorrect. I think that's a really, biologically, we know, red wavelengths, near infrared wavelengths, they're all causing some type of biological effect. To me, based on Bob's work and with other things, it just looks to me like that, as you say, various biological processes are enhanced efficiency when they're exposed to the longer wavelengths that occur in sunlight. Those longer wavelengths can't be generated in the body. They actually have to come from the sun. And, bear in mind that, we're not saying that there's something special about the photons that come from the sun. They're still photons. They have the wavelength, they have the energy, all that. But, people need to realize that the amount of energy being generated or being delivered to the body from sunlight is the single largest energy input into the body. And the vast majority of that, especially when you get into the body a little bit of distance, is on the near infrared and the shortwave infrared. And so I think what we're trying to say is that you have to look at the near infrared and the shortwave as being adjusting, ratcheting up our activity. It's kind of a little bit like what happens when you have a fever. The body changes its operational point. Why? Because it gives the healthy cells an advantage over the pathogen. And so you're more likely that the pathogen dies when the body's homeostasis level goes up, whatever you want to call it. The same thing happens when you walk out into sunlight. You walk out into sunlight, all of a sudden you are exposed predominantly to this near infrared, especially if you're outside in around nature, because you're getting this huge amount of reflection off of all the plants, leaves, and the grass. Even the dirt has a higher reflectivity in the near infrared than in the visible. So it is just generating, when we were outdoors underneath the trees in the forest, we are operating with an excess, probably the highest level of near infrared that you can get to ratio to visible.
Yeah.
Visible, to that photochemist's point, anything that happens, any photon that is shorter than 500 nanometers or whatever, has the ability to break a bond, but it has the ability, you can't predict, the body can't predict which bond it's going to break.
Yep. Yep.
So I look at it from the standpoint of saying that the purpose of the near infrared is to enhance, like a fever, anything else, is to enhance the body's ability to deal with the fact that we need to be able to see, we need to be able to generate vitamin D, but that process is not something, we literally shed our skin every 20 days because of the effect of those shorter wavelengths, and, develop this sacrificial layer that goes away. Now, but to then turn our environment into something where you don't have that near infrared component puts the body at a disadvantage. And over time, that causes, as I believe, is causing a lot of the modern maladies that we're doing and that we're seeing in the thing. Overlaying on top of all this is what I believe is really amazing and a clear indication that it's important are all these structures, nanostructures, that the body is generating or plants are generating to optimize the efficiency of taking advantage of these different wavelengths coming from the sun. And, like I say, the chloroplast to me is just such an amazing example of the optics and how the nanostructure affects. Because as we've shown, the people have known for a while, well, I should say, we now have the capability with our TEMs, transmission electron microscope capability, that we can actually start to see that there is this periodicity inside our cells. Mitochondria has periodicity. Anytime you generate a spatial, a period where you have a high index, low index layer, and you repeat that more than one time, you are modifying where light goes, where the photons are actually going. And there's just so many structures now that are starting to be seen that, because all this needs to be done on 100 nanometer or 200 nanometer scale, which the body does all the time. Like I say, the chloroplasts are just the most elegant thing I've ever seen, where they're actually generating these kind of structures. And literally within the chloroplast, you could argue that it is a little solar cell that is capable, that has directionality. It has all these other benefits that allow the incoming light. One of the things that Berkerov over in Russia showed is that the structure, ignore everything else, simply the structure of the granums within the chloroplast rejects the green component. Why did it reject the green component? It rejected the green component because photosynthesis can only operate within a certain narrow temperature range. Green doesn't do any good for chlorophyll A or chlorophyll B. Chlorophyll A and chlorophyll B have red and blue components. That's where their main absorption bands are. So within this optical structure, it is creating a little dielectric mirror because of the periodicity and the index difference that rejects the green, sends it back out, because any green that gets absorbed in that area will degrade, will increase the relative temperature and is unnecessary for the chlorophyll. At the same time, that same optical structure, when you build a periodicity like this, the high index component localize, when you get to the band edges of this optical structure, dichroic, you'll find that the red and the blues are localized right in the high index layers. What did the plant do? It put chlorophyll just in those layers, and they call it a lumen. And so what it is, rejecting the green and localizing the red and the blue specifically in the structures that contain the chlorophyll A and B. Why would it do that? It's doing it because it gives us the maximum efficiency per unit volume. That's my opinion or my hypothesis. But it, to me,
he's still trying to recover from this.
I am. I think this is the coolest thing in the world. And but what it literally is doing is it's building structures that localize in a specific absorber just the wavelengths that it needs to do what it wants to do, are to do it. And what's interesting is that like cyanobacteria have chlorophyll, but they don't have this periodic structure. I believe, my hypothesis is that the reason that with the advent of being able to make this more efficient, get more energy per unit volume, it allowed the cell more space to add in all the things it needs to go multicellular. And what you'll see is that this structure is available in all the higher order plants. And it's just kind of, it's almost like an evolutionary thing where you go from, I got a chlorophyll, chlorophyll's great, how can I make it better? And that's what appears to have happened in these structures they're in. Now we're seeing, you can see similar structures in mitochondria. It's a different kind, but you can see it. And then you can start to see all these different structures in particles and distributions. But to me, what is the most fascinating thing is that we cannot replicate what the body does on the scale it does and do biochemistry at the same time. We are infants as far as what's going on. And to think that this structure, which correlates quite well with all our telecommunication, the whole idea of using periodic structures is the basis of all our telecommunications. The plants have been doing it for millions of years. And we think we're so stinking smart. That's the part that gets me.
There's this idea that non-chemical communication has to be present because chemical communication is way too slow. It's way too clunky. It's not directed. It's kind of governed by Brownian motion, which just doesn't work when cells need to respond quickly and in a coordinated fashion. And it sounds like these nanostructures that you're talking about, and I'd love to know a little bit more about what they are if they have been identified. But it sounds like in the literature that I've read, there are mainly two things that have been suggested for non-chemical communication. One is light, and that's probably through microtubules that have these quantum properties. They're able to use tryptophans to basically, like a fiber optic cable, connect different mitochondria in different cells and shuttle light somehow. And also fields. So I think both of them are probably happening simultaneously. But are these nanostructures, do you think they could be involved in sort of capturing light and using it in a way to communicate in a non-chemical fashion?
I have no idea. But I do believe this. I do know that the body has the capability to build nanostructures, and you can look at, like I say, I posted some stuff on LinkedIn here recently, but you can see very clearly, and it's been known forever. The butterfly wings, they're not making blue and green by pigments. They're making it by structure, with basically no absorption. And that is one of the things I would argue very strongly, that it is a natural progression to go from dyes and pigments to nanostructure because it inherently is more efficient. It's why we do what we do with telecom. Very small changes in refractive index on a period generates a Bragg grating or a diachroic mirror that we understand quite well at this point. But the body's been building those kind of structures, and how it uses that to either localize at a particular thing or communicate across a distance, I have no idea. I do know that I used to do antenna design, and two resonant antennas can if you get the periodicity or the structure of it very close to the same, then they will talk to each other. Yeah. And they will resonate in response. For the distances we're talking about, it doesn't make much, it's pretty easy to think about it that way.
I think, Cameron, there's a point to make here. I think if you look at the history of understanding photosynthesis, I mean, it took a very long time, over 200 years, to figure out what was going on. The recent work on photosynthesis at the quantum physics level is beautiful stuff, and it's revealing processes, phenomena that 20 years ago we've never dreamt of. It's an extraordinary process. Now we're talking about getting light into complex animals. We're not going to solve this problem at the level of detail that they understand in photosynthesis at the moment very quickly. It's going to be a long, hard process to figure out all the processes that are going on. I think at the moment we have to talk about general principles and the overall energetics of this in order to get clues about the kinds of things that are going on. And I think I'd like to come back and reiterate what I said 10 minutes ago about if you're thinking of homeostasis in your body at a temperature of 37 degrees centigrade, the photon energy associated with that is very, very low. And so if you're given even near-infrared photons from the sun, these are high energy bullets. I mean, they're super high energy bullets compared to anything you can do by thermal motions in your body. And so even though there are few of them, you don't want too many, otherwise you'd disrupt your body, you'd heat your body up. And we're not talking about these solar photons heating up your body. Your temperature won't change very much when you sit in sunlight, hopefully. It might close to the surface, but your overall body temperature won't change very much. But you do have access to these little bullets of very high energy, effectively very high energy photons, which can interact with the biomolecules and change their state. So, it's the fact that we always think of infrared photons as being low energy. They are low energy by visible standards, but they're extremely high energy compared to the state of your body at 37 degrees.
So let me ask you this. I mentioned Glen's publication with Mike Powner earlier this year on basically giving red light therapy for 15 minutes and then showing that it ameliorated the blood glucose spike compared to controls. I made a video a month or so ago suggesting that if you were to do this with traditional hunter-gatherer populations, you wouldn't see an effect because they're not deficient in those solar wavelengths. Do you think that you would see a difference? Because I think what we're seeing is a response to deficiency rather than, seeing a beneficial impact. I think we're just seeing getting up to the bare minimum response that our bodies should be working with all the time.
Yeah, I think that's a very good point. And I think I said in the last point in the notes I sent you, we're not trying to invent therapies. We're trying to restore the status quo. And if you try and do experiments with young athletes to see the effect of infrared light, you probably won't see anything because they're working perfectly well, thank you. You have to look at old geezers like us in order to see a difference in what happens. We age, rather our mitochondria age. It's our mitochondria that age. Mitochondria control the rate at which we age. And as we're aging, I'm talking about us two rather than you, as we're aging, we can have a very significant effect on our mitochondrial function by using infrared light. But all we're doing is restoring the status quo. It's just the same as going out into sunlight. I'm sitting in a room here, which, I do have one LED light on here, actually. It's a special LED light, but it's still an LED light. But I don't have direct sunlight coming in my window, but I have an olive tree outside the window, and the olive tree is radiating me with near-infrared light. So I'm in fairly good situation at the moment. But yes, it's a very good point, and we have to make this very strongly. We're not sitting here discussing therapy. We're not here discussing medicine. We're here saying we could live much better just by putting ourselves in the right environment more often. There's nothing to stop us doing this unless we're on night shift in a hospital or something. We're just restoring what we've evolved under before.
Yeah, I think one of the things that people need to look at it differently. We're suggesting that unlike the pharmaceuticals who treat a particular disease with a specific pill, I believe that, we have the opportunity to provide address a broad range of modern maladies by simply putting back what was always supposed to be there in the first place. And, that's what I think is the real power in this line of research is that, like I say, you can get a pill to do one particular disease, and I'm not knocking it. It works to some extent. But if you have your body in its best position that it was designed for over millions of years, then maybe you won't get that malady in the first place, or you won't get it much later in life than what we're seeing now. And that's my biggest concern with what's happened is that we took something that the body assumes it is always exposed to more near infrared than visible. And we didn't just take a little bit away, for a lot of people, we took it all away. The window glazings that we have block the near infrared and the UV from coming in if you meet DOE requirements. The lighting, they made the assumption that the near infrared had no value, so they got rid of it. And then the displays that our kids spend all their time looking at, that children do not go out and play outdoors. Their sports are all mainly indoors under artificial lighting. So we're looking at the largest reduction in solar exposure in human history. This is bigger than what happened when they went through rickets. It just happens that, we've done it in a way that nobody can notice because their eye response is so limited that we think that nothing happened. And then we go the opposite direction where, I got to go get some sun. So I go out and I lay on a beach and get burned badly and fight, all kinds of skin cancer issues that we're not suggesting that's what you're supposed to go sit out under a tree. I keep on saying my grandpa was a dairy farmer. He wore a straw hat, had a long sleeve cotton shirt, pair of overalls. When it was lunchtime at high noon, he would go find a shade tree, eat his lunch, go back out. That's not what we're doing now. And it is a crime, in my opinion, that we have taken away what the body is using. And all we're doing, really, at the end of the day, all we're really trying to do with the work we've been working on, things we've been doing, is to convince people that what we've been exposed to for millions of years had a purpose. And you can't just take it away without an unintended consequence. I'm in favor of saving the planet as much as anybody. But if you make people sick, you didn't save a single watt of energy or a joule of energy in you doing what we're doing. You actually are wasting energy and causing unbelievable amount of grief if we really can show all these things. And it's going to be a combination, as Bob said. This is not a simple thing. We're literally looking at what I believe is truly quantum biology, because you have to take the wave effects, you have to take the particle effects, all that into account in order to even think about explaining or understanding what the body's been doing. And like I say, you start looking at some of these structures. Why go to this trouble? Why would you do that? Because it gave them an advantage on survival. That's what it boils down to. And it makes it more efficient in one way or another, or allowed them to do something that they could use. And what I think is just so elegant about the whole system is that plants needed red and blue. They took it. They only took the red and blue. They rejected the green. That's why your trees look green leaves. They go into the near infrared. They look white as snow. All that energy, all those photons that Bob's talking about, are being given to us when we're in nature. We took it all away when we went indoors. So
I think that's
we haven't talked about diseases at all. And all of these diseases we're talking about are diseases of aging. We talked about the young people and the older people. It's the diseases of aging that are coming as a result of this infrared starvation. And, you can list the diseases of aging yourself. I mean, type 2 diabetes, obesity, dementias, and so on, all the way down. All of these diseases of aging are the result of mitochondrial dysfunction. And so it's not a single disease. It's not a pill for a single disease. These are all the diseases of aging that result from the gradual decay of mitochondrial function. All we're trying to do is to bring the mitochondrial functionality of people back to the level they could expect if they had a healthy environment. And I don't just mean a healthy food environment, but a healthy light environment. We should use the language, I think, of, you need a healthy light diet. You also need a healthy food diet, but you need a healthy light diet.
Well, that's why I think it's so important to dig deeper into this International Space Station work. I mean, what immediately happens? Sunlight, for some reason, or sunlight in general, is always lowest on the list. It's the microgravity. Oh, it's the diet. Oh, it's this and the other. Well, then, I don't have microgravity in a submarine. I don't have microgravity issues in you look at where we're seeing clear indications of mitochondrial damage. And it's in those situations where we minimize the amount of solar exposure. And they're kind of like canaries in the coal mine. Everything's a function of how much. Mm-hmm. And, what we generated unnecessarily. I mean, it'd be one thing if there was really a benefit, but let's be honest, we're not seeing a huge benefit associated with switching over to LED lighting. What's happening is everybody's putting more lights out there. We know this from clear data. So it's kind of like it's a false misnomer that that we're doing something beneficial by getting rid of critical parts of the solar spectrum. And that's the part that kind of frustrates me in this whole thing is that I'm like I say, I'm in favor of helping the planet any way we can, but let's be honest, and green technologies have to meet, in my opinion, a higher level of scrutiny, because you're changing significant portions and you could be affecting the public health. And that's what I think is going on.
Yeah, look at the costs. People are worrying that if you have to change white LEDs into something else that emit more energy because you need an extra spectral component, that can be done. It can be done very easily. Scott knows how to do it very well. And you've got one next to you at the moment. It's very easy to do. Do you think of the financial cost of the degrading public health around the world at the moment? This will far outweigh orders of magnitude more than the little bit of extra costs that you would have to put into changing the light bulbs.
Changing
the light bulb is not the only thing. We're trying to stop the imposition of glass, which rejects all the healthy light that we need. We understand that, in order to thermally balance buildings without spending too much money on air conditioning, we're going to have to be careful about how we do that. But that's the real problem we need to be tackling. How can we build buildings that are much healthier than the buildings we have at the moment? What do we have to do? We have to consider the glass transmissions. And we have to consider it over a very broad range of wavelengths. We're not just talking about optical and near infrared here. There are a lot of animal and plant nanostructures which know about what to do at 8 or 10 microns in the mid-infrared. You can invent a structure which has direct sunlight shining on it, and then actually the sunlight cools it, because the structure is such that it transfers this visible sunlight into wavelengths around 8 to 10 microns and radiates out into space, where there's a transparency window which sees the cold outer space. Outer space is, 3 degrees kelvins. You can radiate into that at longer wavelengths, while cooling something which is in direct sunlight. There are amazing structures that have been developed by even butterflies do this. Butterflies do this. Butterflies control their temperature by absorbing in the visible. They have black wings, incredibly black wings, which absorb in the visible, and they radiate any excess energy they don't need in the mid-infrared to keep them at a constant temperature. They control their body by the balance between absorption of visible light in the visible spectrum and radiating energy in the mid-infrared. So we can do this. We can have intelligent. In the future we can have intelligent windows which, let in healthy light, generate electricity. You can make almost transparent solar panels, generate electricity. They can adapt to different lighting requirements inside. You can have very, very smart windows. They may be expensive, but you can have very, very smart windows that do all kinds of things to control the conditions in the building, provide you with healthy lighting, provide you with energy for cooling, and so on. It'll all come in the future, I think. We have the technology now to do this.
Yeah. And even more, another aspect of the whole thing is that I think that what really needs to happen is a re-education. As I said, most people, when you say sun, they think about a sunburn. And it's really more a function of understanding, wear a hat, walk under a tree, sit under a tree, don't go out and sit yourself down on the beach and get a French fry going. We need to understand the difference in different ethnic groups. They have much different needs from that standpoint. And, it's been one of the most biggest tragedies associated. I believe that, there was a reason that the majority of I think it was like 95% of all disease transfers occurred during COVID for people that were indoors. They're around other people. But I would argue very strongly that there's clear indication that the ability of the body to fight off disease is tied in with its state of health and how it's, how it affects whether it's in sunlight or not in sunlight. I believe that my personal opinion is that the body is much more resistant to disease transfer when it is exposed to sunlight, kind of like a fever can have the effect of taking out pathogens and relative to healthy cells. So I think there's just so much to learn, but I think we almost need to develop. There you go. We almost need to develop.
I'm just about to go outside in the sun. You can see the clothes I'm wearing. I wear a thin jacket and a shirt. Okay, I'm wearing trousers which absorb ultraviolet. I can go out and I can sit in the sun with my hat on so I don't get my nose burned, and I can keep out the blue and the ultraviolet that might damage me. But all the infrared gets through this. And you've seen my pictures. I'm sure you've seen my pictures. The infrared gets through this with no problem. So my whole body is being irradiated by infrared from the trees outside, direct sunlight. I mean, I'm in a super rich infrared environment, and I'm not going to get sunburned because I protect my face and my body is protected by thin clothes. I'm not going to go and lie on a beach, but it's a no-brainer. It's easy to do this.
Yeah, and but I mean, there is a general fear. I know parents that they will not let their kids do anything without putting a ton of sunblock on, and rather than teaching them that this is good sun, this is bad sun. This is times that you need to be a little more cautious, and other times that you need to. You're at 4 o'clock in the afternoon. Go have a good time. You're not going to get the same thing as you did at noon. And in fact, the infrared levels go up in the process. So And like I say, there's a big difference between whether or not you have white skin or whether you have dark skin. And we need to start taking and looking at that a little closer and understanding what the differences is. One of the cool things about Glen Jeffrey's that I always thought was amazing about his experiment is he created a stressor, he measured it during the stressor, saw a change in the thing, but what was he looking at? He was exposing a very small area of the skin to red or deep red, and at a level that well within what you could get when you're outside in some ways. But he saw a systemic change. And this gets to your comment about communication. Is the communication the fact that all the platelets that were being exposed at that time had mitochondria in it, and those were running at a different rate or generating something different, and then getting pumped around through the body, to where it told everybody else, hey, I'm under attack, I need to have some help, whatever? We don't know, but there is clearly both a local and a systemic response. And we need to start understanding, how much area does it take? How much near infrared does it take to make a big difference? What time? One of the other things about Glen's experiment is that you can after a certain point, there's a diminishing return. This whole concept that Bob's talking about of this homeostasis level, okay, I got this going on, and so we're going to move to this point. And we're going to stay at this point for a while, and you can keep pumping, but that's the best I could do. So this is where we're at. And, keep pumping in a bunch of extra photons, wasting energy, isn't going to make that much difference. But over time, next day or something like that. One of the great cool experiments that they did was with some of these near infrared beds with athletes in China, the women's basketball team. They exposed them over 14 days to a certain amount over their entire body with their eyes covered. And they were actually seeing not just melatonin changes over the 14 days, they actually measured entranced speed of their ability to perform. Their performance levels actually increased. So, people can have no problem understanding or saying, well, you need to eat the right food or you need to drink enough water or things of that nature. But for whatever reason, sunlight, I guess because it's available, people don't take advantage of it, but it's available. They tend to ignore it and don't believe it makes. That's why I think it's so fundamental that what we're trying to show is, as Bob said, this is not a treatment. I'm not trying to get everybody to go sit in front of a panel. I'm trying to get them to go back to something that gives the body its optimum advantage. It doesn't guarantee they aren't going to get disease, but if your body is operating at a higher level of performance because you've gotten significant near infrared over the course of the day, and even into, what gets me is that even at night, it's mostly near infrared,
Yeah.
and and the other thing is that what we've created is this in my opinion, toxic environment. Everybody hates blue, and I understand that. But artificial blue is not blue. I can walk out and be under the blue sky of the sun. It's almost, it's a huge ratio of near infrared that's going along with that blue. That's not what we're doing. We make artificial skylights that have blue. They're blue, nothing else.
Mm-hmm.
That's not nature. That's not what blue is in nature. And yet people say blue is bad. We wear glasses because blue is bad. The blue coming off our screen, blue coming out of our artificial lighting, the blue that comes in through our windows now is not nature's blue. And we almost need a different name for it or something.
Yeah, I think the key point here is what we're experiencing with our indoor lighting situation and even like you say with the glass, what we've created is not a change in magnitude, but actually a change in kind. It's not comparable in any way. And in order for us to be able to live optimally in these conditions where we're spending over 90% of our times indoors, I think we'd probably have to evolve a new system of energy metabolism to cope. Like you said with Glenn and Mike's paper, I saw a lot of these red light panel companies, touting the paper saying, hey, look how good red light is. And I'm sitting there going, no, this should not, cause a knee-jerk reaction to buy red light therapy devices. It's the canary in the coal mine saying, look how broken our light environment is. Look how deficient we are. That even 10 minutes is, 10 or 15 minutes of this, light supplement, so to speak, is enough to improve the basic functionality, when essentially what we've done is we've met the minimum basic requirements for life to function properly. There's nothing optimal about it. It's just getting to the expected level of exposure, these environmental vectors that we're supposed to have contact with. And we've, completely lost it. Go ahead.
Yeah, I guess I would just say that, and Glenn knows this better than anybody, is that, you're literally looking at just one biomarker.
Yeah.
The body is doing everything simultaneously. It has, while that may be great for glucose or CO2 generation, or, in those particular things, as you say, the body's got, all these different things going on that it's having to optimize survival based on, and trying to pick one biomarker, without, and not understanding how it affects other ones, it gets to be hard. And that's why I keep on saying, as we get more and better at all these biosensors, I give Glenn credit from the standpoint, he's one of the few papers that actually measured during a stressor what's going on. But, it's almost like we need to, at the same time, be looking at, well, what's cortisol doing? Well, what's melatonin doing? Well, what's, the calcium flux or whatever? There's just so many things that are going on simultaneously, fixing. It's kind of like taking a pill for the pharma. Okay, I'm going to go fix my one issue here with a red light therapy unit.
Yeah.
We're going to try and optimize it for duration and time.
Yeah.
Or we've decided we want to have the highest THC level in marijuana, so we're going to optimize everything around. Well, is that good or is that bad? It has a different effect. One of my big gripes is that I can't get a decent strawberry to save my soul anymore. Well, why? Because I believe they've taken out, they've optimized one thing. I want a big strawberry. I want it to be nice and red. Do I get the flavor? No, I don't get the flavor. Do I get, the longevity of storage? Nope, I don't get that. But we keep on doing these things where we're thinking we're smarter, or we're optimizing around one element, and we give up something else. And, I want my flavonoids back. Give me a break. So.
Bob, I wanted to ask you about far from equilibrium thermodynamics and dissipative structures, because I think this ties in quite well with what the mitochondria is doing. And I don't know if you can help me out with this, but it's just been an idea I've been really fascinated with in the last few months. And in your paper that you did with Glenn, the astrophysics of Earth, you note that near-infrared light can increase membrane potential. And this seems to be something that decreases with age. It seems to be a primary marker of the mitochondria is losing its ability to hold that proton gradient and separate the charge. And I'm wondering whether you've considered the body's ability to store, capture, and dissipate energy in a way to maintain complexity in an environment where it has to be adaptive in changing conditions. I'm not sure if I've made any sense with that, but maybe you can try and grab onto what I'm saying.
I think I see what you're getting at. I have two kinds of answer to that. One is that the process of controlling the potential, the electrical potential gradient in mitochondria. Yes, that is an age-dependent process, but I don't understand the functioning of the elements of the electron transport chain well enough to understand exactly how you control that. I understand that the ATP synthase, this rotating device which spits out 3 molecules of ATP every time you rotate it, that can operate in both directions. It can accept protons coming down through the gradient and generating ATP. It can also operate in the other direction to build up the potential gradient. I mean, I know people who know much more about this than I do, but I'm not the right person to really answer that question. What I will say is, going off on a related track, this idea of a thermal equilibrium and other kinds of equilibria is very common in astrophysics, where I come from. I mean, if I'm trying to study the atmosphere of a star, the model that I would build of a stellar atmosphere would be something that was not in thermal equilibrium, but would be close to thermal equilibrium.
Yeah,
it's it's an equilibrium-like state where, to a first approximation, everything works as if it's in equilibrium. And the equilibrium is determined by the kinetic temperature of the atoms in the stellar atmosphere. So you have a kinetic temperature, which in the sun is, about 5,800 kelvins. The kinetic temperature varies with height in the atmosphere. But if you look at the outer layers of the stellar atmosphere, the equilibrium of those outer layers is determined far less by the kinetic temperature. It's very low density in the corona, for instance, or the upper chromosphere. The equilibrium of those atoms in the outer layers of the star is much more determined by the radiation field coming from the photosphere, and much less by the kinetic temperature of the atoms themselves. And in particular, if you go and study interstellar nebulae in astrophysics, the only way you can understand the radiation coming from an interstellar nebula is to build a model, a mathematical model, which is called a photoionization model, where you look at every state in every atom, every electronic state in every atom in the nebula, all the elements in the atom, and you form an equation, just a simple equation for that state, which is the rate at which electrons come into that state and the rate at which electrons go out of that state. And they can come into that state in different ways, and they can go out of that state in different ways. And you do that for every atomic level in the whole ensemble of atoms in the nebula. And this is what a modern photoionization model does. It's a huge model in a sense. It's a complicated model, but it's not complicated in principle. It's just a whole set of linear equations, tens of thousands or even hundreds of thousands of linear equations, which you have to solve simultaneously in order to understand the radiation coming from the nebula. And that's quite different from the in the stellar atmosphere, where you can use what's called local thermodynamic equilibrium. It's a kind of approximation to thermodynamic equilibrium where radiation plays a role, but a much smaller role. Now, I think biology is much more similar to the nebula in that the interaction of the photons from the sun with the body is very much like the interaction of the stellar photons exciting an interstellar nebula. And in order to understand what's going on, you're going to have to write down all these equations. All the biomolecules have energy levels which have a rate of electrons coming into them and a rate of electrons going away from them. And you have to solve all of those simultaneously in order to understand the biological effect of the radiation field from the sun. Now, this is new to biologists and certainly to medics. This whole idea is new. It's very familiar to astrophysicists. It's very familiar to people who run fusion reactors, where they have to do similar calculations for understanding the state of the plasma in a tokamak or something like that. So it's perfectly possible to do this. It's just at a different level from what's operating in biology at the moment. So I see an evolution in biology to the extent that you will have to, some people at least, will have to work on this kind of model, which looks at all of the interactions of photons with biological molecules under all these different circumstances and works out what exactly is going on. And it takes a generation or two to develop these models. You can imagine huge amounts of atomic data that go into these photonization models. The amount of data and the quality of data has improved gradually over the years, but it would have been impossible to do this in the 1920s, except in a very simplified form. But now we have these photonization models, which are extremely sophisticated. And that's what we use to understand the distant universe. Look at the James Webb Space Telescope and all the spectroscopy they're doing of forming galaxies in the very early universe. All of that stuff is being analyzed using these photonization models. So we know what's going on. We can measure the abundances of the different elements in the gas at the beginning of the universe very reliably by using these models. But this is not in the mindset of biology yet.
Yeah.
But I think before we get a full understanding, we're giving isolated examples of the way photons might interact with molecules in our body. I mentioned the singlet triplet oxygen, which I think is a particularly interesting one, but there will be many others there. Before we understand this in detail, we will have to go to that level of understanding the details of the interaction of the radiation field coming from the sun with the body. And of course, those are not in any way in equilibrium. Your body equilibrium is at 37 degrees. The solar equilibrium is at 6,000 kelvins. So they're way out of equilibrium. So it's a non-equilibrium model that you'll have to build in order to understand the biology.
Doesn't it also it also defines what life really is?
Yeah.
I mean,
life is the process of solar photons entering the biosphere and then maintaining the high energy quality. I mean, a photon is a very low entropy thing. It just has an energy, and it gets into the biosphere, and it will initiate all of these sort of interactions that we've been talking about over the last hour or so. That energy coming with that photon will pass through this. It's a pinball machine. You're putting a photon in the top. It's bouncing around and doing performing all these functions and gaining points for you. And eventually it's exhausted. It's coming out as a long wavelength infrared, i.e. waste heat.
Yeah.
And life is the process of watching that degradation of high quality energy coming in from the sun, gradually contributing to the process of life until it finally comes out at the end as junk heat. That's what life is. Life is the energy flow of photons, solar photons through the body. That's how I would define life.
It's funny you brought up the issues that they're seeing with the people living in space stations, far away from the influences of Earth. I saw a paper talking about this exact problem of all the issues that they're having with astronauts, and it was basically a new idea about explaining the Fermi paradox, which is basically any civilization that makes it to the point where they're able to make themselves comfortable. By making themselves comfortable, they've detached from the very forces that made them capable of sustaining what is life. And I think that's they were looking at this from the viewpoint of the complete detachment of the electromagnetic influences of being on Earth. They're completely out of that. They have their circadian rhythms are all messed up. Their light exposure is all weird. And of course, they get all of these issues, and they thought maybe this explains the Fermi paradox because, obviously the more civilization gets built up, the more you can detach from the very forces, the more very stresses that built exactly what you are.
I think I know the people you're talking to.
I mean, you're Alistair Nunn and Jimmy Bell.
Exactly. I'm part of the Guy Foundation now. I mean, I go to the
wow.
I go to the talks. So
I've been reaching out to all of these guys for a while, and none of them have got back to me.
this. I currently have their space health report on my desk, and I'm contributing the section on radiation, on photon radiation.
Yeah, the Guy Foundation has been, a really big source of information for me, because they are talking about all of these things that I'm very interested in, these non-chemical communications, biophotons, and all these types of things. So, and it all just ties in so well to what we've been discussing here and in these light-life interactions.
Yeah.
And yeah, it's just absolutely fascinating.
I went to lunch with Jeffrey Guy in his house in Dorset a couple of weeks ago.
I'm very jealous then.
I went to lunch with him in his pub, which he just sold to a tenant. But yes, and we are talking about all this stuff, and I'm attending those lectures now, and I'm on their working group on space health now.
Oh, that's brilliant. That's absolutely brilliant. Yeah, I've been watching a lot of their videos. I can't believe the content that they're putting up for free. It's unbelievable. Scott, I wanted to ask you maybe something a bit more esoteric. Have you heard about, this is very controversial, I'm not sure I believe it because the evidence seems to be a bit lacking, but there's a doctor, I think from Mexico, who has published a fair few papers suggesting that melanin can catalyze, melanin and light can interact to split water the same way that in the first step of photosynthesis. And I've had a lot of people asking me about this because the papers seem to be written in a peculiar way. The citations are a bit weird, and I was wondering if you've heard about this possibility that's been put forward called human photosynthesis. Yeah, Bob.
Right, can I just hold? I have to go for a pee, so can you all?
Yeah, that's fine. That's fine.
I'll come back and listen to what I don't envy Scott the question, so I want to.
We'll pause. We'll pause. We'll give him some time to think.
You can edit it out, right?
Yeah, absolutely. Yeah, it's funny. The podcasts don't usually go this long, so never had the issue of the pee break before.
Well, we're getting old. Give me a break.
Yeah.
Okay?
You've been getting quite popular. I've seen you pop up on a bunch of different podcasts recently. People seem to be,
like I say, I just appreciate the fact that you got me linked up with Bob. I mean, I've been learning so much. I mean, he approaches it in an entirely different perspective, and Glen is like he's like the father of the group in some ways. He said, "No, come on, guys, you're getting a little bit carried away here."
No, honestly, having played a role in this is, one of my proudest moments, because I actually think that what you guys are working on could really change people's lives, and to think that I played a small part in that is absolutely enormous to me. And it's the whole it's the whole point of this podcast, is just to try and get the word out there, and to think that I've played even the smallest of roles in that is absolutely amazing.
Well, what amazes me is how difficult it is to get people to look at alternatives and go through a discovery. I mean, one thing I do know is something about discovery process, and it's messy and it's frustrating, and you got some CEO that's sitting there wanting to have some definitive answer, and you say, we don't know enough to give you a definitive answer, but this is the trend, type thing. So anyway, but we can start back up. You're back, Bob. I'm good.
I'm much more comfortable. I can have a glass of water now.
Okay, let's go. It's clear that melanin is a unique material. Optically, it's unique in how it absorbs strongly in the UV, and by the time you get out to around 700 nanometers, it's basically dropped back out. I can't reproduce that easily with any dye set that's known to man at the present time. But there's clearly been work. There's a gentleman down at Temple that showed that he could make a solar cell out of melanin. If you can make a solar cell, you can probably crack a water molecule. I would argue that that the interface where melanin, the other thing that's unique about melanin is it's provided in a little granule rather than, and so if you look at that optically, longer wavelengths, you have a different transmission from a bunch of little granules that are all very much the same size. You have a certain level of periodicity when you have granules that are all the same size. You see them localized in places where there are index of refraction differences between, there's about a 0.05 index of refraction difference between the epidermis and the dermis. Why? Well, in the structure that's generated, for years, everybody said that the structure that's in between the epidermis and dermis was basically for mechanical adhesion. Well, optically, those little divots have clearly localized in the photons in place where those little granules are. That's kind of curious. The other thing is that if you look at solar cells, the structure, even the spacing, the roughness that we put on solar cells looks almost identical to what you see in the epidermis dermis. And to enhance the effectiveness of being able to absorb light. So there's all kinds of indications that there could be effects. I personally like the idea associated with from Professor Zaire over in Stanford, where he's showing that all these, including incandescent bulbs, are all capable of generating hydrogen peroxide. Why do I think hydrogen peroxide is important? Because I, like Bob, if I had any hair, would actually be seeing, I'm seeing a little bit of white coming in. And, I did some of these other, looked at some of these other effects that are going on with the generation of vitamin D. And so I would argue that, there most likely is some level. It turns out that one gentleman showed that the interstitial fluid between our cells is 650-fold higher hydrogen peroxide than what's inside the cells. So one hypothesis is that the hydrogen peroxide is generated. Niederhammer showed that when you wound an animal like a zebrafish, hydrogen peroxide actually localizes right at the wound. It's the first thing that happens. And the differential is, and so, the idea that, there's a variety of plants that localize or generate a protective outer preventing pathogens coming in. There's a lot of different ways as you can look at it that clearly indicate that melanin has its ability to generate either free radicals or to split the water atom. One of the things that we've had a lot of conversations about is the reactive oxygen species. Well, when you look at the lifetime of some of these reactive oxygen species, there's only one or two that can stick around long enough to affect things on a biological scale.
Yeah.
When a singlet or something like that comes in, its lifetime is in the nanoseconds. Okay, well, if its lifetime is in nanoseconds, it can only move nanometers to get to do something. But if it cascades down into something like hydrogen peroxide, now you're talking about it being able to do things on a time and a spatial scale that is compatible with biology. So you almost have this effect of, in the same way that Bob's saying about how photons go down, some of these reactive oxygen species, we need to think about them on a time scale rather than just on a biological effect, because literally it can't get to this part of the cell in time, but hydrogen peroxide can. And, I would argue that I like to blame my gray hair on the idea that my cells are just not being able to handle maintain their hydrogen peroxide delta, and so I'm getting gray hair. I have to blame something on it, but that's what I think.
That's super
I'm past the
interesting.
grey hair stage.
Say what?
I'm past the grey hair stage.
I know. Well,
there's another Cameron. There's another interesting little side story here, which you can edit out if you want. But if you look at a hen's egg shell, it's often hen's eggs are brown.
Mm-hmm.
They're actually brown because they have little specks of purple in the matrix, and the purple is protoporphyrin IX. Now, why do hens coat their shells with protoporphyrin IX? That's a puzzle that's been around for a long time, and biologists have hypothesized all kinds of things, like it makes the shell stronger and so on. But protoporphyrin IX can be toxic if you shine light on it, and all the stories about porphyria.
Specifically, blue light.
Well, actually, you can shine visible light. It doesn't have to be blue. It's all there. The various Q bands of the porphyrin extend through the visible. There's a strong blue band, the sorry band, and there are a number of Q bands as well. But the point is that the puzzle of why the hen coats its eggshell in protoporphyrin has been around for a long time. And it does it like an inkjet printer. As the egg is going down the oviduct, there's a printer head around, and it imprints the protoporphyrin on the eggshell as it goes down the oviduct. And there was a paper published several years ago now, which I came across by a Japanese group, who said that what happens is when light shines on the protoporphyrin on an eggshell, it generates this toxin which kills bacteria, gram-positive bacteria, and so it's a protection mechanism for the interior of the egg against surrounding bacteria, and it works extraordinarily well because you can keep eggs in the fridge for weeks, and they don't get infected with bacteria.
I remember you telling me that the mitochondria make protoporphyrin IX because they make heme, and that when they're exposed to visible or particularly blue-rich artificial light, they can generate singlet oxygen. And you had suggested at the time that you think this process happens at night, which is a potential reason why exposure to artificial light at night might reap some of its negative consequences on mitochondrial function. And this has always fascinated me because I wondered if that had any impact on blood dynamics, like hemoglobin counts, or even to some extent oxygen carrying capacity.
Well, we're going into the realms of hypothesis now, but yeah. I think the toxin is actually singlet oxygen, and if you excite a porphyrin into one of its basic excited energy levels, that can exchange its excitation energy with oxygen, with a triplet oxygen molecule, to excite it to a singlet state. So this is the way in which the porphyrins are excited in photodynamic therapy to kill cancer cells. Mm-hmm. You inject a porphyrin-like substance into the cancer region of the tumor, and then you use that porphyrin as a medium for generating reactive oxygen species, which kill the cells. So it's an intermediate state. You excite the porphyrin with light. Yep. Now they have red sensitive porphyrin-like molecules. So they excite with red light. It generates reactive oxygen, and excuse me, that's what does the damage to the cell, tells it to commit suicide. So yes, and the hen's egg, it generates reactive oxygen on the surface, and presumably acts as an antibacterial.
That's so fascinating.
I remember.
Oh, I
I've
used to
also,
go collect the eggs. My grandparents were farmers, and I used to go collect the eggs every morning. And quite
yeah,
often they would be very, very freshly laid. And yeah,
yeah.
we never had any issues with, getting sick from the bacteria on the shells.
But that was a paper by a Japanese group, which I found very impressive. I mean, the other story I tell is about earthworms when they come out in a rainstorm onto a concrete surface or road surface, and the sun comes out, they all die.
Mm.
And everybody says it's because they dry out. It's actually because they have Protoporphyrin IX in their skins, in their integument, and it's the toxin generated by the ultraviolet light or the blue light on the skin of the earthworm, which poisons it.
Wow, that's fascinating. That happens all the time at my house.
Yeah.
Yeah. One thing I wanted to ask as well, it seems quite clear to me that there are quantum biological processes happening, particularly in the electron transport chain. I think the presence of iron sulfur clusters in complex 1 is quite a giveaway. I think that these redox centers all through the protein complexes are most likely engaging in they're tunneling electrons, I suspect. And for the reason these quantum processes were thought to be impossible was because there's too much sort of incoherent noise, I guess you could say, within a biological system. And it seems even with the advent of the quantum model of photosynthesis that there are ways that life sort of silences or dampens the noise to allow quantum processes to happen. And I've come across the idea of a Froelich condensate or a state in which matter is sort of held in this neat ordered state. And I suspect that what exposure to sunlight is doing is helping create this coherence pattern within the cell, and particularly within the mitochondria. And I was wondering, is that an idea that resonates with you? And if so, how do you think how is a state of quantum coherence achieved within the mitochondria?
Well, it does resonate indeed, and in fact, right at this very moment, I'm pondering this problem.
Mm.
The best thing I can get you to do is to actually read Jim Al-Khalili and John Joe, whatever his name is.
I've already read it, and I've invited them both onto the podcast, and I haven't heard back from either of them.
Well, read it again. I read it again over the last few days, and I learned a lot more from it the second time. But
yeah, it's brilliant.
I went to a lecture last week at the local Bath Royal Literary and Scientific Institution by a quantum physicist from Bath University, who was basically introducing the concept of quantum mechanics to a public audience. And he did it very well, very interesting discussion. And he was talking about quantum computers using electrons for qubits, and saying these all have to operate at millikelvin temperatures. You can't get far away from absolute zero and maintain the coherence in qubits. And this is obviously a big problem, big expense in quantum computing. But he also started talking about photon-based qubits.
Mm-hmm.
And they already have chips which handle quantum-based qubits. And I don't know any details. This is a public level talk. But those can operate at much higher temperatures. So I asked him a question at the end, and halfway through the question, I actually realized what the answer was. And it was a very interesting answer. The reason that these photons can perform these very esoteric processes in photosynthesis and what we've been talking about at reasonably high temperatures, 300 kelvins, is because these photons they have so much energy that the noise, the thermal noise in the surroundings, is a low-level white noise for them. It's not a big deal. Whereas an electron at millikelvins, any increase in temperature is a major producer of relevant noise. So, the reason that these quantum effects seem so prevalent in biology, and this was a surprise for the quantum physicists, as is described very beautifully in Al-Khalili's book.
Yeah.
The reason the quantum physicists thought this was complete rubbish was that they hadn't realized that the photon-based phenomena were not nearly so sensitive to noise as the electron-based phenomena, and so it is a very interesting topic. And I think when we think about this radiative equilibrium between the sun and your body in the infrared, those infrared photons are perfectly able to institute quantum transitions, quantum processes, because they're not so bothered by the high temperatures. So they're probably very, very beautiful and elegant processes going on there, which we haven't yet thought of, which are enabled by the same physics as is now understood in the chloroplast, when you can get the energy from the antenna molecules into the reaction center essentially instantly.
Yeah.
It's like the young slit experiment. The wave function is doing the computation immediately to know where to go and to go to the reaction center. So it's a beautiful subject area. I only wish I'd grown up as a quantum physicist to look at quantum biologist to look at these processes now, because I think once biologists get the hang of this stuff, there'll be all kinds of realizations happening about how biology works at the quantum level. But I have another gripe. As Scott had a gripe earlier in this podcast, I'll have my own gripe. Is everybody's saying, "Oh, isn't it amazing that you get quantum effects in biology?" I don't understand. Of course you bloody get quantum effects in biology. That's the way life works. That is physics. That's what physics is. Of course it's quantum mechanics.
Well, it's interesting you say that, because I've tried to use these new AI engines that have come out, and they're quite complex. But the moment you ask them about anything to do with quantum biology, they just say, well, there's it's still, no one really knows whether quantum processes happen in biological systems. And I'm just like, I've got 10 papers right in front of me that are saying yes, that's exactly what's happening. And yeah, it's so obvious, isn't it, that we're dealing with fundamental particles, and of course these quantum processes are happening all over the place. Why would we think that they're not?
Evolution didn't have any problem figuring it out. It's just we're having the problem.
Yeah, exactly. Exactly. Did you have anything to add to that, Scott?
Well, I just think that every time there's a new buzzword, it tends to dilute the science in some ways. I wish it's like heat and temperature and things like that. They kind of start lumping things together. But I think that it's absolutely clear that there is quantum effects going on in biology, and it's more than just getting rid of the blue. Or I just think it tends to get dumbed down more than it needs to be. As Bob said, this is something that's going to take decades to go through and truly understand, and it just needs a lot more time, I guess.
It's very exciting. I think that there are lots of PhD theses that have to be written on these topics, and I think it's a very good time to be a young quantum biologist, because there are lots and lots of things to do, and it'll be very exciting. And I don't think nowadays it's terribly difficult to do. I mean, there are techniques around there, and there are problems that are already formulated that need solving. So I think it's a very exciting time to be doing quantum biology.
Well, what I find fascinating is that if we were having this conversation 20 years ago, we wouldn't even know that there was structure, nanometer structure in some cells. We wouldn't know, some of the effects that Bob's talking about. just the simple, some of his work where he looked at cloud structure or the scatter within clouds and how that affects, it really is this whole thing that the body is doing where photons are propagating around until they find a weak absorber. And then so when you measure the spectra of a cloud, you see that there's a much more absorption or deeper absorption band than what you'd predict if it was just, not taking into account all these scatter. But
look at my Flickr site and search for thundercloud, spectrum of a thundercloud. And you'll see this amplification factor that we talked about in bodies, the scattering, the lengthening of the time the photon spends in a thundercloud means that the light is having a much longer path in the thundercloud than it would if it just went straight through. And this increases the strength of all the weak absorbers. And so you see very, very weak absorbers very strongly in the thundercloud that you would never see if you were just looking directly at the sun with that solar altitude. And
it's just amazing how I think we're looking at so vastly different levels of understanding from the standpoint of we're still having conversations trying to get people to understand that what they see is not sunlight, when it comes out of the bulb. We have understandings associated with how chlorophyll or how these structures are doing things in chloroplast. And, there's just a long way to go. And, like I say, my pet gripe is that we're still having debate of whether or not the near infrared actually goes into the body.
Yeah.
If you look at the majority of the papers out there, near infrared only goes a millimeter. Well, it's because you measured it wrong. When that little ice cube, you can say that, what you have to notice is the minute you put the snowball in there, the entire snowball lights up because light's getting scattered everywhere. That is an absorber in a different kind of way, in that it is distributing these photons deep into the body, and you can't, I don't know how to get it past the problem that, we still have basic papers being written saying that, it only goes a millimeter. It's just wrong. And it's time to, for us to accept that there's more going on than just absorption. There's a lot of scatter. And scatter can be, especially when you start doing these periodic structures, why does it go to the trouble to localize those photons? And you can have some huge effects. We make laser diodes where we put gain media just in certain parts of the periodicity of the structure, because you get localization and a huge enhancement effect compared to putting it everywhere. So I think that we underestimate how elegant but complex some of these optical effects are, and how important they are to tie in with the quantum effects. So,
Cameron, you can do this experiment yourself, and I recommend it. I've got an insect here in a plexiglass. You can see it.
Yeah.
Okay. I mean, I happen to be encased in plexiglass. If you can get an macroscopic scale insect like this, dead or recently dead, and shine optical light onto it and see what happens, and then shine 800 nanometer light on it, near infrared light on it. If I shine near infrared light on this, the whole thing lights up like Scott's snowball.
Mm-hmm.
And at 670 nanometers, it just absorbs.
Yeah.
You don't see anything. But at 850 nanometers, it lights up like a snowball in a laser. And you can do this with your infrared lamp. I'm sure if you have an insect, you probably find insects more often than I do where you're living.
Yeah, yeah, they're a bit more scary where we are. We tend to stay away from them down under. Is that a good distinguishing point? I often try and understand, how to categorize near infrared and infrared. would a good characterization be that near-infrared is weakly absorbed by water, whereas infrared has strong absorption band? Is that sort of the distinction?
Well, yes. I mean, it's a two-sided distinction, I think. One is at shorter wavelengths, below the chlorophyll red edge, 700 nanometers, you get all the pigments because you excite electrons in atoms and molecules. Above 1,000 nanometers, you get the water bands, which absorb increasingly strongly the further you go. So within the 700 to 1,000 or 1,300 nanometers, where the water's reasonably weak, between those wavelengths, you get your tissue transparency window, where all living tissue is relatively transparent. And that's where all the infrared action happens. I think outside that band, at longer wavelengths, as Scott will attest, you'll get effects closer to the surface of the body because you can't penetrate so deeply because of the water. But the interactions of the infrared photons with the water are probably very relevant, including the hydrogen peroxide, which he's just been talking about.
Yeah. Yeah.
So the window is defined by water at one end and pigments at the other end.
Yeah.
And that's where you can get deep into the body.
Yeah, and this is where I think that, I like to define, as Bob says, the red edge as being a boundary on one side. But, getting into the longer wavelengths, doesn't mean that it isn't doing some effect. It's just doing it more localized. And in fact, if you do the math, the number of if you believe in more of a quantum approach, then the number of photons per unit volume are highest actually in the shortwave infrared, what people totally ignore. And because it's so localized because of the strong absorption band that are of water. And, clearly that there's multiple papers that show that the shortwave has sufficient energy to generate hydrogen peroxide. I can do it with an incandescent bulb. I can do it with a 1270 nanometer laser. I can do it, the Russians have shown that very clearly. So, and again, we then get back to, the body's dealing with multiple things and has multiple defenses. There's some indication that, literally some of our protection against pathogens is associated by maintaining a high level of hydrogen peroxide in the interstitial fluid, which I don't think is too big of a stretch to believe. And the near infrared, it just happened, or the shortwave infrared localizes in the outer 50 microns of, is absorbed strongly within that outer 50 microns, creating a very high density of photons, a lower energy photons, but a high density of photons in those other wavelength ranges. And it also, the other pet peeve I've got is that we always have heat. I like Bob's way of looking at it. Is you get down to our body temperature and things happen, that's heat. But everything above that is capable of doing things that we shouldn't underestimate. And, using heat and temperature, we really do go to the point of having a lot of work in the area of quantum biology. You start talking about states. You don't start, temperature doesn't mean anything. And, we just happen to have sunlight and our body are pretty close to a black body radiator, so we can have that conversation about temperature. But when you think about even like the chloroplast, where it's only extracting red and blue from a solar spectrum that's from 250 clear out to beyond 4,000, how do you assign a temperature to that? You don't. You need to start doing what Bob's saying, looking at it for at the individual wavelength of states that are available and how that can translate into affecting things like chlorophyll. So we need to get a much more rigorous approach to how you talk about, and myself included, how you talk about what's going on. And I think that's what quantum biology should be all about, to be quite honest, is just to get more detailed or a more rigorous approach to how we describe things that are going on.
Cameron, I don't know how you want to sort of wind this up, but I think we should. It's that question number 5. How should we react to all this understanding? Because I think we need to give people some idea of what can be done. And I think one of the advantages of this particular topic is there are things that can be done. And, if I use the terrible expression, this is not rocket science. It's not actually rocket science. It's, there are concrete things we can do. And we've covered some of them, but perhaps we should just summarize this. And I think, if one starts off with the lighting, anyone can make a healthy light environment in their house. I do it in my house without spending even a penny.
Yeah.
In my kitchen, I have 3,000 Kelvin LED downlighters on the ceiling, which gives me visible light, fine. And over the kitchen table, I have a set of 3 quartz halogen lamps, which I run dimmed at lower voltage, and they give me gobs of infrared light. And the combination of those two is pretty close to sunlight. It's certainly not exact. There's a bit of a dip around 800 nanometers between the two sources, but it's pretty much like sunlight. And I've had those quartz halogen bulbs in those lamps in my kitchen for 13 years, every day, and none of them has ever blown. So, the low temperature tungsten filaments last forever. And as Scott will attest, tungsten filament is pretty efficient, much more efficient than an LED in the infrared.
Yeah,
much more efficient.
And I think that, one of the problems that you have to be running into that has to be overcome is that there is no sense that there is a problem, and that, I think the problem, that's what you start to see from the space station and the industry has essentially, especially now with the DOE with their new 120 lumen per watt rule coming in, has essentially institutionalized a large portion of the population to be exposed to what I consider harmful lighting.
Yeah.
And, that's where the struggle and what I think is a lot of the motivation. Number one, Bob's situation, the new 120 will eliminate his ability to ever get a halogen. I mean, I hope it lasts another 15 years because you're not going to be able to buy them, is what their goal is. Now, you can get around it, and people are doing that. But, I just wish I knew how much energy was being spent on red panel therapy units, across the world, that all they could do is just walk outside and they'd be much better off. But, it's a problem that we've got to somehow re-educate, I guess, or prove to people that there is a harm being done. Right now, people look at it as red light therapy. Oh, I can go and I can fix something. As Bob said before, that's not what we're talking about here. We're talking about creating an environment that is optimum for, people to safely or get their maximum benefit out of sunlight. And, that's why we do what we do with our bulb. We put it in, have it such that, you can combine the best of LEDs with the best of incandescent, make it so the incandescent can last longer, all those things, and get the right ratios. I personally believe that ratios are a very important component in this whole thing, and that because that's what happens in nature. We are never exposed to visible and UV without a lot more near infrared. Well, someone like Bob is really capable. He understands what's going on. He can do a mix and be fine.
Yep.
But, somebody who's just wanting to get through the day, they just want to screw in a bulb and feel good about it. And that's what I think, is what we're trying to do different than Yeah, I totally agree with Bob. You can do this for free. And the easiest way is just have a regular routine of going outside under a shade tree every once in a while, as much as you can.
Yeah.
You know, so gardeners are winners.
Yeah. I think that's what's so frustrating about this, is because it is actually something that we can fix quite easily, but there is just no desire to fix it because it's not seen as a problem. And yeah, it's frustrating that our vision has been set up this way that we don't even notice. And you know,
I mean, it's really quite insidious when you look at it. Is that we are easily fooled, and the eye is great in a lot of regards, but from an optic standpoint, the vast majority of photons that make it to the retina are in the near infrared, and that there's a bigger optical window in the humor in the near infrared than it is in the visible. So didn't happen by happenstance.
It's quite shocking. Yeah, it's quite shocking when you look at the plots of the spectrum. Scott and I have been discussing this over the last couple of days, and you look at the breadth of the solar spectrum from the atmospheric cutoff at 300 nanometers, where the ozone absorbs, through to 2 or 3 microns, where the water is absorbing everything, and beyond even. When you look at the solar spectrum and you plot the distribution of light coming out of an LED, it's this tiny sliver in the visible part of the spectrum. And now we discover that the glass manufacturers are making glass which only allows that thin sliver of the light to come through into buildings. So we're suffering a double whammy where we're not getting any useful radiation through the window, and we're not getting it from the lighting either.
Well, it's hard because you add on to that the dermatologists are highly motivated to convince everybody to put a bunch of sunscreen on. Sunscreen itself is a filter, auto modifying, and even the basic premise that UV is really the main cause of melanoma, is somewhat up for debate, because there's all these studies that show that people at higher latitudes that are regular out in the sun have a lower rate of melanoma than people who are indoors all the time. So, there's lore and then there's science, and that's kind of what I think we're trying. It's been the goal from day one, is to understand the actual mechanisms, because it's so hard to run controlled, blind studies on these broad issues. So I think the more we can understand the mechanisms, that's why I'm so excited about some of the structure stuff and the biosensors and all that. The more we can actually run real-time tests that aren't, that show effects in real time and at different for a wide variety of different sensors or molecules, then I think we have an opportunity to convince people. And I'm really, to me, of course, I'm convinced, but how can you look at the space station data? How can you look at all this other data that Glen's doing and not say, this is doing important stuff? And, so much of what we're struggling with in modern society are metabolic or mitochondrial based issues. And this is clearly affecting those performance levels of those particular processes. So.
Yeah, and I think something that I find myself saying a lot more is, our starting point should be to look at the biggest changes in our environment over the last 100 years, because clearly those are going to be the drivers of the big changes we're seeing in chronic disease. So wouldn't it be logical to start at the largest changes first? And I think the light environment is arguably one of, if not the biggest changes in our environment. I think more so than our diets have changed. I think light has changed significantly more than our dietary intakes have shifted over the last century. And it just seems logical to me that light is a place to start, because it's relatively easy and cheap to fix if it can be identified as a problem. And like you said before, Bob, the payoff, it would pay dividends to fix this problem from a healthcare point of view. We're spending billions of dollars a year on healthcare. It might even be trillions in the US. I'm not even sure. But it's astronomical, and I think fixing something as fundamental as this, or not even fixing it, but mending it to the point where it's at least not damaging us, would be one of the biggest things we should be looking into. And nowhere more than Australia is an uphill battle against the dermatologists and the ophthalmologists. But I think from the point of view of reaching individuals who are ready to hear this message. We have to reach the people who are ready to hear the message, and also the architects, and and also the scientists themselves who need to be taking this into account. I think it's just going to be a slow process, but I'm glad you guys are on the job, and if I can help, I hope I'm helping, even if it's just a small amount.
Well, I think one of our big problem is public awareness, and we need the scientific papers, but we need public awareness of what's going on. And I think I would just like to reiterate that one of the problems with the red light industry, the photobiomodulation industry, is that it's all focused on therapies for particular problems, and it has a certain sort of snake oil smell about it. And I think it's, for that reason, it's not taken terribly seriously.
Well, I think it's turning light into a drug.
Sorry?
It's turning light into a drug. What we're talking about is we don't want to use light as a drug. We want it to be the foundation upon which our health is built.
We're trying to restore the status quo. It has to be said. We take note of how the planet has evolved, and don't mess with the way it's evolved. And we are messing with it in all kinds of ways. I mean, it's not just lighting; we're messing with it in all kinds of ways. But messing with the planet is not a good idea, as we're discovering at this very moment.
Well, and to Bob's point, it doesn't take much. We have the technology to make this go away.
Yeah.
I mean, it's not like we're asking people to invent, time travel or something like that. But for what we are being forced into a particular situation to a great extent by DOE, or the Department of Energy, and their new standards that they're coming into. They are essentially negating the possibility of providing people, the people that I argue, the people that need it the most, which is the underserved communities. I do the optical, look at the optics of the whole thing on the models, and, how much of the things that we're struggling with are associated with increased anxiety levels, or neurological issues, or physiological issues, into populations that can't do what, you're in the inner city. How can you get it and be out in the park all the time? You're stuck inside and in these glass towers that block all the near infrared. You have all these different issues that these are self-imposed effects, mainly associated, I would argue, associated with comfort or some other things of that nature, rather than looking at it from what is the best optimum environment to put people in. And, I'm like I say, I'm really frustrated right now with the DOE's 120 lumen per watt. There was all kinds of arguments that put forth that there were other biological effects. I know that there essentially threw out a provision for circadian. So if you look at it from the standpoint of just pure math, if you say that every bulb all these bulbs have to be 120 lumen per watt, you make it look just like what Bob was taught you, the narrow band, because you can't afford to provide the near infrared or UV that is part of nature based on this simple little rule. And it's to me, it's criminal. I think that they're, doing things that are I'm sure it's unintentional, but it's just plain wrong. And, in fact, I would turn it around. One of my arguments that I'm working on for this in a rebuttal to the thing is that I believe we actually should be requiring that no light source with greater than 60 or 100 lumen per watt be allowed to expose to children, because that means by definition it doesn't have the near infrared component necessary, and rather than what they're doing now, which is essentially institutionalizing bad lighting or unhealthy lighting for large portions of the population, and it's such a limitation that's not necessary. You can actually you can mix and match different sources and get pretty doggone close, and you can use that to provide great dimming range, improvements in dimming range. So it's unnecessary, and it doesn't really. Even worse, it's not even working. The same space station is measuring increases in light levels of 10% every few years. And that in particular, what they don't realize is that most of those are going blue, high blue content, because they have to meet these lumens per watt numbers. And you're essentially putting the absolute worst lighting system out there as far as insects and plants and people are concerned. So that's my point.
I couldn't agree more, and I think we've got a mountain to climb, but hopefully sometime soon we will look back in disbelief with what we've done with our lighting environment, and worry about the impact that might have had on like you said, particularly our kids. But if we can look back on that in disbelief in a short space of time, then that would be much better than if it takes us 50, 60, 70 years to fix the problem. I hope it doesn't take that long, but who knows? But looks like we can sort of save ourselves. I think that's part of the key, is that the people who are interested and understand, they can sort of opt out of these horrible lighting situations and mend their local environment at least.
Well, one of the things is that I just find, if you thought there's even an inkling that you could enhance the cognitive learning, I mean, there's multiple studies that show that cognitive learning is better. There's multiple studies that show that being near a window in a hospital has benefits compared to the one not. Even if you're an inkling, you don't have to understand every reason, but why wouldn't you?
You don't have to understand.
It's not like they're saving the planet by doing what they're doing. That's a great storyline. But if I'm even taking out one work day a year, I just paid for all the benefits associated with switching over to LED lighting.
Exactly. Yeah. I think that's a pretty nice way to sum up. I mean, I feel like we've come pretty full circle with covering this. There's a lot in here. There's a lot we've gone through a lot. Is there anything else you wanted to add, Bob, Scott?
I think the problem is it's the same problem as we're having with the climate change issues. It's a matter of language, and it's a matter of information. I mean, the language is often not carefully considered. I mean, global warming and climate change, I think, are very poor representations of the problem that we're facing. And I think we need to be careful here to choose the right language to describe the problem we have. I mean, it's the solutions in a sense are so obvious. The knowledge is being gained so quickly that the the standard metrics that can be used by industry to make big financial decisions are difficult to fulfill those conditions when things are moving so quickly. We can come along and say to the glass manufacturers or the lighting manufacturers, look, you really shouldn't do this. You've got to change it to that. They won't listen to us until there's a solid base of acceptable scientific literature which can be used as a basis. And we have to catch up with this quite quickly, I think, because the first question people ask is, give me the paper, tell me, where should I look, what can I reference? And in a subject which is changing so rapidly, it's harder to pull that together. But I think the public awareness, in a sense, we have to give the public awareness before all that stuff is necessarily caught up. And this is why, podcast is a very good way of doing this, because, we can give our honest opinions and we can tell you what we know at the moment. We can't tell you what we don't know.
Yeah.
To get all the ideas that we've just discussed firmly into the scientific literature will take a while.
Yeah.
I mean, it's a slow process. And it may be difficult in some areas. People may choose not to like what we're saying. So, I think we need all the help we can in making people aware of these problems and the effects it'll have. The basic problem is that most of the biologists who are senior biologists around at the moment grew up in an era when they had tungsten lighting in their bedrooms and in their kitchens. And so nobody was aware of this problem because we had plenty of near-infrared light surrounding us all the time. And indeed, the fact that the plentiness of it, the fact that it was so dominant, is the reason we're losing it now, because it was not efficient at making visible light. And I agree, we all agree it's not efficient at making visible light, but it's so vital for our health. And when people come to realize the cost of the health degradation in our societies is crippling us. And in the case of the UK, I mean, the NHS is on its knees. When I talk to a doctor in the NHS and say, which disease should we try and get rid of first in order to save money in the NHS? They say type 2 diabetes. Everyone I've asked has said type 2 diabetes. Yeah. Type 2 diabetes is directly linked to mitochondrial function. We've already shown, Glen and his group have shown that you can reduce blood sugars just by shining infrared light on people. In a way, it's a no-brainer. We have to react. We have to react from the bottom up. We can't wait for the politicians to propose solutions.
Exactly.
We can propose solutions to the politicians, but it's a very hard route up through that channel to get it accepted as.
Yeah, well, I would just make the point that I think that there are a lot of people. Just Cameron, you've been great and all that are looking for a solution and believe that there's something going on here, but this change from from sunlight over to this artificial light, whether it be due to flicker or spectrum or whatever. We're finding with our bulb that we're getting more and more people. And surprisingly, it's mainly women that are responding. And you get these response where, immediately he slept a little better. It's not going to be that there's going to be some great magical effect that everybody's now going to be happy and joyous and all that. And that's why I think the definite, as Bob says, the use of words is very important. And when I first started this, I was more in the mind of being helpful. Now I'm trying to, as you said, Cameron, I'm trying to get rid of something that I think is harmful. Mm. And that's where the acceptance needs to go. Because unfortunately in our society, once something is deemed harmful. Then there are unpleasant mechanisms, but mechanisms where these companies will have to respond. And, part of that is going to be associated, as Bob said, with good papers, good science. Other part is just going to be general sentiment by the population. As Bob said, this isn't hard. This isn't rocket science. This is pretty simple, straightforward approach. Will it solve all your problems? No. But why would you put yourself at a disadvantage? That's why, Rogers Seaholtz in some of his videos, his viewpoint is that if I can reduce hospital stay even slightly, it pays for anything I do. He's not trying to use it to make the person, he's still doing all the medicine stuff. Don't get me wrong. But just adding this little component, taking his patient outdoors for 15 to 30 minutes, and that patient feeling better, even if it didn't physiologically change much, if it changed his attitude, there is a huge biological effect. We know that. We don't have feelings just based on, or some esoteric thing. There's a biological thing that the dopamine came up, the cortisol level dropped, the melatonin levels were piked up when we do an exercise. All those things affect the survivability or the basic health of individuals. And, I keep going back to we've been talking about the physiological effects, but neurologically, if you feel better, you do better. And it's hard to quantify that, but it's a real effect that, the majority of the people that we sell our lights to, that's what I get a response. I slept a little bit better. I feel a little bit better. It wasn't quite as agitated, autistic, some of the autistic children, did it solve their problem? No, it didn't. It's simply a tool. But, why wouldn't you? I mean, that's what I keep on trying to figure out. Why would you do the other than the fact maybe it's a little cheaper? I don't know. For a mother who's dealing with an autistic child or something like that, how much is it worth for them to sleep a little bit longer, or feel a little bit better, or, not have quite as much issues to deal with? And I'm not claiming that that's what we do. I'm just saying that's what we're really looking for here. We're looking for some way to reverse a terrible trend. I mean, if you plot some of these mitochondrial or metabolite, these diseases, this is not a good road to be on. And we need to reverse it. And that's one thing I guess I would argue is that there needs to be a major sea change somewhere. There's not going to be a magic pill that's going to solve this. This is an environmental issue. And the space station, the submarines, night workers are just clearly indicators that the artificial environment we're creating is toxic. And it's time to stop it and reverse course. And that's what really go ahead.
We heard somebody on BBC Radio about 6 months ago. Both Glenn and I heard it independently in different places. It was one of the chief medics in the National Health Service talking about degrading public health and the fact that there was lots of ultra-processed food around and the various factors contributing to this. And he just said at the end, and there's something wrong with the office environment that we don't understand. Yeah. And, imagine what Glenn and I thought at that point. Yes, there's something wrong with it. We know what the problem is.
Yeah.
How do we get that? How do we get that out there? I think, just to my closing statement would be for me to ask you, Cameron, and you to ask your podcast viewers, perhaps, get your people to describe where they feel happiest and most contented in their lives? What situations are they in when they feel happy and contented? Now, if you ask me that question, I would ask, and I would have asked many years ago before I even started thinking about this topic, when I'm standing in a forest in sunlight, possibly under the trees in an arboretum in a beautiful garden or something, I feel more contented than I feel at any other time. Now, what is it about being in a forest under the trees in peace and quiet? And I don't know, but the fact is that that's the place where I'd rather be. I go on garden visits. I'm a member of the local gardening group. I don't garden so much, but I go on visits to gardens, beautiful gardens. And I go into these gardens and I feel wonderful. I mean, it's just, you feel so much better. And the fact that the Japanese go forest bathing, you may think it's a fad, stupid idea, but they've got it right on the nail. That's where you feel best. You're not being damaged by sunlight because you're in the shade. You're not overheating, but you just feel better. You feel so much better. And that's the effect of this. Your body mechanism works so much better.
And I think that's just the normal physiological state for what we are. I think the reason we feel good is it's just good relative to, being inside. I think what it really is just normal. That's how we should feel all the time. And yeah, I mean, it's remarkable how big a difference it can make to your affect. Not just to your metabolic health, but just clearly the way your mind works when you're in a natural environment. It is just remarkable, and I'm sure everyone who's listening to this is going to agree that whether it's underneath a waterfall or in a forest or like you said, even in a garden, the effects are huge, and I think this is just a universal feeling across everyone for that exact reason. It's our normal physiological state.
Scott already said it at the beginning, but Newton sat under an apple tree. Why did he sit under an apple tree?
Yeah. Because his brain worked better, right? But right. I do think that unfortunately the only real way to get this to change is for a grassroots approach, because there's just so much invested in a basic flawed philosophy that we could get away with 10% of the solar spectrum and be healthy. Because there's always going to be somebody in the population, be it astronauts or people in nursing homes or people stuck in the hospital, where if we don't change, give them the opportunity to get the full spectrum, then they are going to be at a disadvantage. It makes it very hard because, you can walk outside in 15 minutes and you can generate some vitamin D and make you feel a little bit better. But we don't really understand what the time constants are. How long does that benefit last? And what other things are going on? So it's kind of like we have this easy way of fixing it, but we don't exactly understand how much of it we need. And it's kind of like we need almost like a daily lot of necessary amount or something like that. I don't know what you call it, but daily allowance or something like that.
Yeah, but the point is, we're doing it by getting them into a natural environment, and therefore we've evolved under a natural environment. Yeah. So we're not putting people in danger by doing this, because we're not inventing something new that they've never experienced before. We're just putting them in the natural environment. And I think that's the way I'd like to end this, by saying, we're not making therapies, we're getting people in, we're providing a reason, an underlying reason why you should get closer to the natural environment if you can.
I like that.
Do it sensibly, but it costs you very little, if anything, and it will not do you damage.
Yeah.
What a
I agree.
brilliant way to wrap up. I think that mirrors my notion of this conversation exactly. You just stop being a zoo animal. Just live an outdoor life. You don't have to get directly in the sun, but you just have to be outside like we're supposed to be. And the grassroots movements are happening. I think, Scott, what you're doing with the NIRA bulbs, a good friend of mine has moved to Nicaragua. He's setting up a gym, an outdoor gym on the beach, to make sure people are working out not under artificial light. I recently met a guy who's working on a startup there. They've made something called the Daylight Computer, which is a tablet that has no backlight. It's no flicker. It works kind of like a Kindle. And it's just, I think this type of technology, this more organic technology is exactly the grassroots movement we need to bring awareness to the fact that we are meant to be outside and we're not meant to be exposed to these alien lights, these hyper novel lighting situations that we find ourselves in. So hopefully this conversation is going to be a part of this grassroots movement, getting people to understand how important this stuff is. And I would like to take this moment to thank you so much for coming on again and giving me some of your time. This has been such a pleasure for me. And like I said, the fact that I was able to sort of introduce you to has easily been the highlight of my journey in this space for sure. And I hope you continue to produce work together that's going to help a lot of people. That's the way I see it.
Well, thank you.
Thank you.
Thank you so much for listening, everyone. 50 episodes is a huge milestone, but hopefully it's just the beginning. Whether you're new to the podcast or a listener from episode 1, thank you so much for the support. As always, all of the relevant links are provided below. So please subscribe, like, and do all that good stuff, as it really helps me reach more listeners, which increases the likelihood that the people I want to speak to will get back to me. Another reminder is that I have a Substack now where I go even deeper into the ideas explored here on the podcast. It's a great way to support my work if you can. So thanks again, everyone. Take care.